The universe is calling me. It speaks both day and night. It's full of dark and light. And I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space, fields and forms, math and voids. It all sings with one voice. It's boundaries set, foundations laid. Sound was heard, matter made. Solar systems from afar. Names and numbers for the stars, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space. It's the Lord's.
Hey everybody, welcome to Skytour live stream. It's me, Marc Antonio, and I'm running a stream tonight that's a little bit special. We're going to take you, I will be taking you through an application online that you can get to and use for free that will give you the most incredible views and information about the moon. It's full of most of the data we've ever received from the moon through the various missions, from Clementine to Ranger to Surveyor to Lunar Reconnaissance Orbiter, the Apollo missions, and many more. So that's what tonight's about. We're going to try and show you that. And the reason I'm starting with a browser is because we want to start to show you how to find it. So if you go into Google, okay, in fact, I'll just go to google.com. We're going to just get started right away, okay? Here we are. So you go to Google and you type in the following: LRO QuickMap. See that? LRO QuickMap. Hit enter. And the first entry that will come up will be probably this one, LROC : QuickMap. And you click on that, and it takes you to this. And you say, what's this? Well, it's a moon. You can move it all around and explore it and zoom in, zoom out, right? And you say, well, what good is this? You know, if you don't know where anything is, what's the point? And what is this application? What you're staring at right here, besides the moon, is the most complete repository of data on the moon in existence. You just don't know it yet. And once you start, and I'm going to warn you right now, once you start doing this, you're going to be stuck for days. You may forget to eat. The first time I discovered this and started crater diving and doing things at highest resolutions known to humankind, it was like I got to check out all these weird places on the moon I've always wanted to look at. Okay, so I'll show you that tonight, and it's going to be really, really interesting. We are definitely going to, this is, again, we call this a cloudy night stream. Why? Because out in Arizona, we have a front moving through with some clouds. So we don't have the ability to do this right now. I do want to say hi to everybody who's here early. Thank you so much for coming. I want to say hi to Renee Cruz, who was first. CND Boy next. Okay. Lubo in China. What's up, Lubo? Calibos is with us. That's our friend Michael. And Tim F. is with us. Mike Hedrick is with us. Who's that Skyter live stream guy? What the heck? Okay. C&D Marco, and let's see, Christopher Thompson, nice to see you. Thanks for coming. You don't want to miss this. This is the coolest thing. And then let's see, we have Daisy and Zoe Amethyst. Nice to see you guys. Do you have Lane with you? Let me know. And Old School is with us. Good to see you. And Alice Pooper is with us. I just love that name, Alice Pooper. I don't know. Okay, Eric's with us. Eric's Automotive Diagnostics and Repair. Nice to see you again tonight. James Hyatt, good to see you. Michael Galea. Gladys, hey, that's nice to see you. You haven't been here for a while, so good to see you now. Okay, so looking at the screen here, and by the way, in case you haven't thought of this, please consider being part of our Patreon, or consider going to skytourlive.org, our website. I don't have those on the screen right now because tonight is just a night to showcase the moon in a way you've never seen it before. Okay, so let's get started. When you first get into this application, you go here, and the browser brings you here. Let me just shrink it a little bit to get us on this path here. There we go. Okay, so this right here, okay, we can now, over on the left side here, you'll see there's a couple of icons, okay? The icons, we'll start at the top. This says switch projections. It's a little bit off, but that's okay. I can actually work on that for a second. Let me just see if I can bring that down for you. Well, that's not what I want to do. No. Okay, so let's go back. All right. So, here's what we're going to do. Let's look at the projections. All right. And it shows you all these different projections of the moon. This is the near side. This is the orthographic near side, the face-on view of the near side of the moon. Now, you might wonder, well, what about the far side? Yes, there it is coming up. This is the orthographic far side right there. You'll notice something really incredible. The far side of the moon has way more craters than the near side of the moon. I mean, when we look at the near side, we see this. We see all these dark maria. These are lava lakes that flooded the surface of the moon in its early development, right? But the far side doesn't have that. The far side is littered with these craters, and we'll talk about why that's the case a little bit later. All right, so we have the far side and the near side. We also have the North Pole of the moon. This is the North Polar region of the moon. Okay, now some of you are already saying, oh, but didn't we send spacecraft to the South Pole of the moon looking for water for potential bases that we can put in there someday? And the answer is yes. And that's something that we'll talk about too. and that's this, the orthographic south pole. You notice it's pretty dark in here. That's because at the north and south poles of the moon, the sunlight never hits the bottom of some of the craters because they're really at the poles, and the sunlight is hitting like horizontally and isn't getting down into the craters because the moon doesn't rotate like a normal planet or moon may. Okay, and now so we have this equidistant cylindrical model. This is if we want to just look at it as a flat model of the moon. Okay, I don't use that. Stereographic North Pole and stereographic South Pole. Okay, I don't use these too much. However, one that I use a lot is this last one, Lunar Globe 3D. Check this out. Okay, at first glance, it doesn't look like much different from the other one that we looked at, this other projection, except for one thing. You can move it. You can move the moon around and check it out. This is the side you're familiar with seeing. Okay, right? Now, you can zoom in and say, wow, look at this. You can zoom in. Now, watch this. This crater here. Who knows what that crater is? I know some of you know. That's Plato. It's about 60 miles across. If we zoom into it, okay, you're going to notice something happen. As we do, the data changes, and we start to get better and better resolution. All right, and that resolution is changing as we zoom in, and then finally they overlay it with new data that shows it even better. Now you'll say, well, wow, that's pretty cool, but you can also use the middle mouse button on your mouse, the middle mouse button, and do this. Check this out. Ever want to know what it looks like from inside Plato? There it is. That's how it looks inside Plato. You can spin around using that middle mouse button and see what it looks like from inside Plato Crater. Now, this is pretty cool, right? And there's so much to this online application that we can't cover it all tonight, but I'm giving you the things that can make you miss dinners and so forth because you're going to be so excited about traveling the moon in this new way. And scrolling with the mouse wheel takes you out, and there you see that data inside Plato Crater. Mouse button, again, we're in the 3D globe of the moon right now, right? So there you can see Plato as it looks from above, as if we're orbiting over it, all right? And there's all kinds of features that are available to us here, but here you can see how it looks from above Plato Crater. Isn't that something else? Really, really cool. And remember, make sure you ask questions if you got any questions out there. So what do you do with this tool? What if you didn't know this was Plato? Okay, well, there's things you can do about that, because now this is our projections tab that we looked at. Now let's look at this one. This is the layers. Holy cow. Look at all these layers that are available to you. Now, you're not going to do most of these in all likelihood. But you have the geologic features. You can actually look at geologic features. You can look at the Clementine data. You can look at Luniserve. You can look at the Chandrayaan, the Grail, the Kaguya, Lunar Prospector, all these different missions with their different data sets and the way that they particularly took them. You can actually look. All right. Now, one of the things that I would like to show you that's really important is when you come up here, right? So if we do this, these are all the layers. One of the layers at the very top is overlays. Okay. So you click overlays, and these now are the overlays. One of them that's very important is nomenclature. Like, what is that thing we're looking at? So we click it, and now look, Plato. And look, all these other craters are being labeled as well for you. And you can see them. And again, we're in the 3D version of the moon. But going back to projections, just for the time being, let's go back to orthographic Nearside. And there's Plato from that perspective. Okay, remember the mountains you might see below Plato? What are they? Well, it's Mons Pico, all right, and Pico G, that's a crater. And then we have Montes Tenerife over here. So you can see all these little craters. Now look at this right here, just as an example. Look at these craterlets. When have you ever seen these craterlets? You haven't. You never have, and the reason is because, what are they? Well, these are little craterlets that were formed from a one impact, and then that impact splattered material out on the moon, which went out some distance and then re-collided with the moon later on. This is a secondary impact location. And it probably wasn't from Plato because they're in a line, so it might have come from some crater farther away, one way or the other. Could have come from Pico B. It hit like this and splattered stuff out, which then hit down here and boom, did that. So there's some pretty cool, interesting, and there's data out there you can find, probably even in here, that will show you that. Now, as we zoom out of the moon, you'll see there's an awful lot of named places. So you can find everything. Here's Mare Imbrium, the Imbrium Basin. This is a gigantic impact location, right? And then over here in Sinus Iridum, this is another impact crater, right? This was probably a crater. And then when Mare Imbrium was formed, it flooded into this crater and filled it in, okay, with lava. So what's under here is probably the remains of an ancient crater, but it's forever covered in molten rock now as a lunar soil, right? So if you ever wondered what everything is at the edge of the moon, like over here, you know about Aristarchus. I think Aristarchus is the brightest spot on the moon, and this region here is called the Aristarchus Plateau. Okay, and when you look at Aristarchus, you'll see it is really quite bright white. And when you zoom in, you'll notice that it's getting clearer and clearer. And as we zoom in further and further and further still, okay, we are right now at 0.5 meters per pixel in our camera view. Now, if you look down at the bottom right there, okay, it says 0.5 meters per pixel right there. If we zoom out, okay, now we're at about a meter per pixel. There's 1.24 meters per pixel, right? And so it shows that we're zooming in to get the highest resolution possible. You can see these this shocked strata from the impact that created Aristarchus, right, in here. And this crater isn't small at all. So you ask yourself, well, there's a lot of misconceptions too about craters. People always ask me, why are craters always at the same depth? They're not. Okay, well, how can you prove that? Easily, and we're going to tonight. I'm going to show you how to do that, and you can do it yourself. Okay, so let's take a look then at the tools. And if you go down from these overlays here and the layers, okay, we leave that behind, and we just come down to the draw and search tool. You notice you have some tools over here, okay? Well, you can actually draw an area line if you like. You click and draw a line around like something you want to select, and say how many square kilometers are inside the base of Aristarchus crater, and you can do this and get a rough idea, and it shows you inside, all the data inside here, okay, and that's the feature info, and the area right here, it says it's 225,916 square kilometers inside this area that I just put in here. So we're talking a fairly large area, right? And then you hit the delete by hitting the garbage can, the red garbage can, and it goes away. But here's something even more fun. You just grab this line and you click and drag and then double click. Now, what did I just do? Well, what I just did was I created this line here, and it tells us a lot of information. Now, let's do this. So now, when you hit, you click on inspect. So here's feature info, that was what it starts with. Then you hit inspect that line. And look at this. Look at this. It tells you all the depths and the slopes. The red are the depths and the blue are the slopes here. Okay? And look over here. You'll see that as I move this through here, it's got a little crosshair going through. So when we get to the peak right there, that corresponds to that little point we have in our image up there. So you see, this tells us right here, okay, what's the depth right here? If you look up above, you have a green dot. That's this blue dot. You have this blue dot, you have this yellow, and this red. This is the terrain height. Now, it's in meters, but what's it measured against? It's measured against the mean radius of the moon. Think of the mean as, it's not an average, but it's a similar type of construct to give you a starting point. So many things can be below the mean radius of the moon, and many can be above. So right here, this terrain height, if you look in that red dot up there, it says minus 3,122 meters. The bottom of this crater is 3,224 meters below, all right, the way it's listed there, below the mean radius of the moon. Okay, now you come outside over here, and we're at minus 1,432. Let me just take us out to there. We're at minus 882 meters below the mean radius. So even this whole area, okay, is still below the mean radius of the moon, right? So it has to be higher. And that's consistent when we look at the other side, because the other side has lots of craters and lots of elevations. So it's sticking up above that mean sphere, okay, that mean sphere that we stick in the moon as a mean starting point for our radius, okay? So this is the coolest feature, and when you look at this, you say, oh, that's at minus 3217, as it says, right? Okay, and you're looking at this number right down here, okay, right there, and this, let's see, let me say right here. That's the number you're looking at, is the one that's under the word terrain height there, okay? And so when you move across this, it's changing because we're climbing the wall of the crater. So on the side to the right of the crater, that wall right there is actually lower than the left side, okay? And that's why this left side over here is called the Aristarchus Plateau. It's a higher elevation, and then it kind of levels off, all right? And if you want, you can then say, well, hey, let's get rid of that, and let's actually do a bigger line. Let's go into Herodotus and come across and go through the center of Aristarchus and go all the way to this area here, which is out on the plain, out on the Mare, all right? Now, it's not going through Herodotus directly, but it's going through enough. So as you can see, it reaches the floor of Herodotus, and Herodotus is actually at a higher elevation than the bottom of Aristarchus is. Isn't that crazy? So right there, you see that the craters are not all the same depth at all. Isn't that cool? So this tool helps you see that. It allows you to analyze the data in ways that you never could. And by the way, again, coming back over here, remember we have our projections, right? We have our layers, and then we have our tools. Now in our projections, okay, let's go to 3D globe, all right? And let's look at this with the 3D globe. Okay, so we're still here, all right? There is Aristarchus, but now we're over it, right? We're centered over it. Now, again, being that it's a 3D globe, we can rotate it out of the way, and if we come out far enough, you can see that we can just rotate it right around. This is kind of what we see kind of on an angle, right? Because we don't ever get to sit over Aristarchus crater like this. But as we zoom in, now we can actually see how the craters are laid out relative to each other. All right? So you can see just from like there that Herodotus is slightly smaller than Aristarchus. But if you wanted to know how much smaller, it's easy because you can have many more of these lines. Let's say we put one here. Herodotus. Okay. All right. That's 32 kilometers across right there. All right. And the reason you can see that is right there, up in the upper right. Okay. Across the bottom of Herodotus, it's 32 kilometers across. And then here, looking at Aristarchus, we'll go from the outside wall to here. Outside wall. Okay. And now you can see that Aristarchus, excuse me, is 35.997 across. So that's pretty cool. And that's actually how all this works. All right. Sip. There we go. All right, so you have all these measurement tools that you can use. Now I'm going to show you something that you're absolutely not going to believe. And this is going to be the part that knocks your socks off. If this didn't. Okay, and we're just looking at the fun stuff. Okay, there's a lot more fun to come. So watch. Let's suppose we do this. We draw a little square around Aristarchus. See how that's doing it? Okay. All right, and then we bring it back up and complete the square. Double click to complete the square. And now we have that, right? Here's all our stuff as before. Okay, and you'll say, well, that's not helpful to me. But if we go into other up there, see other right there, up there at the top? Watch this. Other. 3D printing. Oh, yes. Oh, yes. There it is in 3D. Export the 3D model. This is probably the most valuable thing that I'm showing you right now. Give it a nickname. Okay. Aristarchus. Well, that ain't Aristarchus. Aristarchus, right? As you can see, I've done this before. All right, and then say build. And it's building a 3D model that you can download as what's called an STL file. And this STL file can be thrown on any 3D printer, and you can make yourself a model of Aristarchus Crater. I've been making them for years. And I've been using the curated data from the United States Geological Survey. And now it's included in this map. This is the coolest thing. This is the coolest thing. So here is Aristarchus, and you will get this, and if you notice down below, it says vertical exaggeration. Well, we can actually make the vertical exaggeration a little higher. You see what I mean? We can actually go like 7 times. If you wanted to see a really exaggerated view of what this thing would look like, you can do that. All that does is make your 3D model thicker and bigger. And I typically will do 2 times at the most. And that way you can see some good detail. This doesn't give you as fine a resolution as I use. Typically, I'll use something like 1.2, 1.3 vertical exaggeration. Sometimes I'll stay at 1 depending on how deep the crater is. So now what you're seeing here is a way to create a 3D model from this QuickMap here. All right. Now this QuickMap, as I mentioned, there is just so much to it. All right, so much to it that you'll be hard pressed to get a lot of sleep once you start using it. I can tell you that. All right. So that said, I'm pretty sure that you might want to see some other things on the moon right now, and one of the places that we're going to go, and I'm going to actually go back to our Nearside projection here. Let's do that. Okay, orthographic Nearside. And I'll go into our layers. And I'm going to turn off the names. And I'm going to go to something else that you're going to really enjoy. Anthropogenic features. Anthropogenic means human-made. Now, you didn't see anything change. But if you zoom out, okay, as you zoom out, you're going to see that there's red dots. There's some more. See that? So what is this? Well, if you click on them, you'll see this. This is Apollo 12 is here. And as we zoom in, and zoom in, you'll notice that there are these lines. You know what those are? Astronaut tracks. We went to the moon, guys. No doubt about it. I don't want to hear the crap. So, one thing you can do, actually, when you look at anthropogenic features, is you come in here and it says opacity. This is good because you can actually, take these things down to nothing. So here is the Apollo 12 lunar module right here. You can see it, and you can see the shadow, all right, of its base, right? They went this way, they went that way, they made a whole bunch of tracks out here. They created and deployed experiments. Okay, so here we see over there's experiments put out there. And I picked this one in particular because over here in this crater, there's actually a satellite, a lunar lander that we sent up there years ago called Surveyor 3. And here is Surveyor 3. Surveyor 3 is it landed in this crater, and the astronauts from Apollo 12 walked around here, walked down the slope, and actually touched something that had landed there years before they got there. Isn't that crazy? Wow. And to Darlene Vieras, who's watching, here are the tracks right here. You can see the tracks that the astronauts made so long ago on the moon. Right? Long before you were born. She's 10. And Alicia, her mom, is in the chat here. And as far as the tracks, this is as far as we can zoom in on the tracks when we're in this mode. Okay, when we're just in the 3D model, in the 3D map, you can zoom in tighter. However, 0.5 meter per pixel is the optimum amount for what we're doing here. I do want to show you something though. Let's zoom this out or take this out. You see this dot right here? That's the Surveyor, and there's its shadow. See that? There's its shadow. Crazy, huh? Here's a boulder. There's its shadow. There's the lunar module. There's its shadow. All right. Now, in some of the landing sites, the Lunar Reconnaissance Orbiter, which is still mapping the moon, was so close. It got down. It was at 60 miles typically. That's why you can see this. It got down to 30 miles, and they mapped. And there's ultra high resolution imagery that's available on the website to see this. Okay, so when you look at the craters like this, one of the things too that you'll notice is that, and Izabela makes a note of it, that the craters look like domes, right? It looks like a dome, and that's something that's the result of an illusion with the eyes and the way the sunlight comes in. A very quick fix is you stand on your head or you look at it upside down, and it will actually look normal. I think we can approximate that by going into the Lunar 3D Globe here. Okay, so here we are in the Lunar 3D Globe, and we're going to zoom in again, and now we can go a little further in, right? And we can also do this, and now you can see the lunar lander. You can see the Surveyor. Isn't this crazy? Right. And if you look at this like we were before, and this looks like a dome, all you gotta do is spin it around. All right. Now those look like craters now, don't they? They don't look like domes anymore. So spinning them around is good. Plus, in this mode, you can actually kind of sift along the surface and see the thing. This is what they saw when they were there. As they were coming in for a landing, the moon looked like this to them, and they landed right there. There's this shadow of the lunar lander right there, and there is the tracks. We can see a little closer, but you notice when I talk about the pixelation, we're in at the farthest resolution point for this data, so it doesn't look as good. All right, but you gotta say, man, this is crazy. So what about if we go to some more anthropogenic features? And you say, well, how do we find the others? Well, we can filter by mission. Okay, we can go say Apollo 11, Apollo 12. Let's look at Apollo 17. Okay, so where's Apollo 17? Let's zoom out and look for the marker. Yeah, so I gotta zoom out now, and I'm scroll wheeling. This is, scrolling with the mouse wheel. All right. So somewhere, and I can't remember exactly where it is, but of course we're in the 3D mode. Let me go into our regular orthographic Nearside image, okay, and do it that way. I believe it's over here somewhere. Let's find it. Let me go back to our Apollo 17. Let me see if I can find it when I zoom out. The dots are so small sometimes you can't see it. What's over there? It was in a highland area, that's the thing, which was really interesting. And they managed to do it, which is really cool. All right, well, we'll come back to that. I don't want to waste your time on this. It's here. But one that I think you'll notice right away, if we go into Apollo 15, okay, there's Apollo 15 and Apollo 17. So let's zoom out a little bit, and let's come in here. This is where Apollo 15 is, all right. Oh, I think I had the opacity too low. Maybe that's what it was. I did. I had it off. I'm an idiot. Sorry, guys. So now I bet you when I pull out of this here, okay, there is the red dot for that. And if I come down here, we'll see the red dot for Apollo 17. Trying to remember where it was. Well, let's go in here. Let's look at Apollo 15 because I'm going to show you what happened here with Apollo 15. So Apollo 15 landed here in this area, and this was a rill. This is a sunken valley. It looks like a vein on the surface, I know, but that's what happens with lunar imagery. And if we again, if we go back and go to our lunar 3D globe, then you can see by coming in here, just by doing this, you can see that we're looking at a sunken valley now. In fact, we can even go in the valley, which is really kind of cool. Check this out. How about that, huh? Look at you guys go. All right, so now here is the Apollo site, the Apollo 15 landing site here. And this one is actually really good because it shows you, here's the Apollo 15 Lunar Module, the ALSEP experiment, the Lunar Ranging and Reflector Array, the LRRR. That's that array with lots of little reflectors on it that they shine laser beams on to get the distance to the moon. That was actually made at the university where I got my degree in astronomy. So we're very proud of that because it's an amazing piece of apparatus which is made of what are called corner reflectors. A corner reflector is a reflector that will return some bit of light no matter which angle you send the light in at. It'll always return something along the same path that the beam came in on. Very important if you're on the moon because you can't angle anything at you. So the Lunar Reflector Array here was able to reflect light back no matter what, laser light, and we could actually detect that, and because it takes just over a second, we can calculate very, very, very precisely how far away the moon is at that exact moment. And as we've learned, the moon is suspected and figured out from mass analysis and angular momentum, the moon is leaving our presence by about that much each year, 3 centimeters. So at 3 centimeters, as it's moving across away from it, it's spiraling away. Now the reason that's happening is because of something called angular momentum transfer. So what that means is, as the moon is orbiting the Earth, all right, it has gravity, and the Earth has gravity. And so you got these two bodies going around each other. And the Earth has a tidal bulge from the tides, okay? And what happens is the moon is actually, the tidal bulge on the Earth leads the moon, right? Because it's big, it's bulky, right? So as the Earth spins, that tidal bulge kind of leads the Earth a little bit as it's being dragged around. So then, as that happens, now from the moon's position, the moon is feeling the gravity of the Earth, but then this additional tiny bulge sticking out further that way. And that kind of tugs the moon faster in its orbit. And the faster something orbits, the faster it goes, the bigger its orbit becomes. So the moon is spiraling slowly away because of our tidal bulge that it is responsible for, in part. The sun is also responsible for it. And because of that, the tidal bulge is leading it. The moon is speeding up, and at the gravity of the moon tugging on the tidal bulge causes a friction that slows down the Earth's rotation. So what's happening is the Earth is losing a little angular momentum. Okay, sorry about that. And the moon is gaining some in its orbit. So because of the presence of the moon, a day on the Earth went from being 4 hours long when Earth was first formed with the moon to 24 hours long, 23 hours, 56 minutes and change. So that's because of the fact that Gladys, I thought that was my alarm. Sorry. That is because of the fact that the moon is stealing the momentum from us and is transferring to the moon. So energy can't be created or destroyed, but you can transfer it. Okay, and that's what's happening. We're actually transferring this energy of angular momentum to the moon. So it's going a little further away each year. It's about 3 centimeters. And you might say, well, wait, can't the moon actually leave at some point? Won't the moon leave the Earth's orbit at some point, and finally we won't have a moon anymore? Yes, that's possible, except that at 3 centimeters a year, it would take the moon longer than the sun has left to exist for the moon to actually leave Earth orbit. And as we've talked about when we've looked at some wonderful imagery of our planetary nebula that we see, like the Helix Nebula, the Ring Nebula, the Dumbbell Nebula, which is so beautiful. When we see these things, we see that there's a lot of gas around this central white dwarf in the middle. Well, the sun is going to be one of these white dwarfs someday, and it's going to expel its outer atmosphere as well. And if that outer atmosphere is hot enough, it's going to fry the Earth. So there won't be a chance for the moon to spiral away fully from our planet. So I think that's pretty cool. Now, if anyone has any questions, please feel free to ask. And right now we're centered on the Apollo 15 landing site on the moon. Here's the tracks. Can't miss them. Can't miss them. Right? And it's a beautiful location, again, in the 3D model, in the 3D moon. It's really something. But because there's no air on the moon, if you come down here, let's go down to the moon level, okay? And let's say we're here and we're looking around, okay? This is what we'd see. Now, that hill doesn't look like it's too far away, right? But if we bring ourselves up, all right, and move away, okay, where's the hill? The hill is over by Hadley Rill, okay? So how far is that hill? Okay, how far is Hadley Rill, that magic little hill? Well, again, we can go to our tools and we can draw a line and say, well, let's click on this and click over here. So how far is that? All right. Well, that's over 2 kilometers away. Look, 2.5 kilometers away, and it's an uphill climb. See that? Right to the edge of the rill. And that is the hill that we were seeing from down below. So without an atmosphere, it's really an illusion and when we look at the moon, it's really an illusion. We see all these features and think they're just right around the corner, but they aren't. Okay, now these mountains, okay, that we saw, I think that it's these mountains that we saw when we were down low. Okay, here we saw the edge of Hadley Rill, but now if we go down here again, all right, let's come down here again. And let's go, oh, there's the lunar rover. Okay, and let's go to here. This is the lunar module. Okay, let's come down again, and there's Hadley Rill that I was talking about. But see this mountain here? Okay, that mountain from our perspective on the moon is going to look like that. How far away is that? It looks like it's just right around the corner as well. I think that's the one I pointed to before. My mistake. I wanted to talk to you about Hadley Rill first. But let's see how far that really is in the moon when we don't have any atmosphere. So, there is the lunar module. Okay, down there. And here's the mountain we're looking at. So how far away is that? It looks like it's right around the corner. So let's click on that and go to that mountain, to the peak of the mountain. 20 kilometers. It's 20 kilometers away. Nice thing about these lines is they kind of show the basic slopes and everything, so it's kind of cool. So when we zoom back in, right down here, come down here. Here we go. All right, so from here, we look up and say, look, that's actually 20 kilometers away. It's not just around the corner. It's not just like 500 feet. And you'll notice that we can't see the base of the mountain. Okay, if we zoom back out here, the base of the mountain is like here. How come we can't see that? The reason is because the moon is only 2,000 miles across, and the curvature of the moon makes it vanish over the horizon. So that's pretty cool. And if you ever have any questions about any of this stuff, I'll be happy to share it with you. I'll answer it for you too. That's kind of what I meant. All right, so I'm gonna just reset now. So one of the things that I think is really interesting about looking at these landing sites is that you have the people that say, oh, we never went to the moon, we never went to the moon. And unfortunately, they're just showcasing their ignorance, because we certainly did. All right, so now from here, let's do this. Let's go like this. All right, and let's look over here. And see what this guy is. Interesting. That's a glitch. I have to say, this application has come a long way, and this is a free browser, which I think is really interesting. Okay, I see what's going on. Okay, so we'll go back to our overlays here. And I see I'm not filtered right now by mission, that's why. All right, because some of these are the Russian rovers and things like that. Doomwalker, you're funny. He says, I've never had a mod tell me to use caps lock before. Well, if you want to ask a question, that's helpful. Like James Hyatt says, at some point in the future, the moon will be locked to one side of the Earth, he's asking. It is now, anyway. So the moon... Okay, we do have what's called tidal lock in effect with our moon. Now, The moon's of a certain diameter and mass. The Earth's of a certain diameter and mass. And the moon is close enough to the Earth such that it can't be rotating because the differential gravity on the moon is such that it's keeping one side toward us. All right, and this came from the original formation of the moon. So it was tidally locked from day one. But it's interesting when you look at the moon, because when the moon, we see it now, okay, one of the things that is interesting about the moon is that we have I think this might be Apollo 17. I want to try and find it. Is that it? Oh, sorry guys, I'm just... that's 16. Okay. And there's Apollo 16. And once again, more fake moon tracks, right? The Apollo 16 rover is right there. Again, we can do what I did before, which was not a good thing to forget about, and that was I got rid of the opacity here so you could actually see that. It didn't go. Let's do this. Let's put that back. Just waiting here for this to come back. There we are. So the lunar rover for the Apollo 16 is there. There's the tracks. And look at how extensive they are. Once we started doing the rovers on the moon, man, we tracked it all up, man. Once we had rovers, we started really going to town. And it was something else. It was just, they could go miles now instead of feet. Apollo 11, they walked, right? And they hopped along a few ways, few distances, a little bit away. And they improved their breathing apparatus. They improved their suits between 11 and 17. The other thing that happened with Apollo 17 is we actually saw the lunar module take off in full color off the moon and head up. So now here's a little trivia for you. When they separated that lunar module that held the astronauts on the moon, the lunar module separated from the base. The base was called the descent stage. That sat on the moon and had the legs. And that lunar module popped off of that and went back to orbit and connected back up with the command module, which had been circling the moon, okay, with one astronaut in it, and the other two were on the moon. Well, when it reconnected to the command module and they transferred back to the command module to come home, what did they do with the lunar module? They jettisoned it, and it went into a shallow, spiraling orbit that spiraled closer and closer to the moon until it crashed. Keep in mind that there's no air in the moon, and the purpose of the lunar module and the capability was to keep the air inside. So it's like a balloon ready to pop, right? Had they crashed on the lunar surface, it would have exploded and gone in a million directions. I don't mean exploding with fire. I mean pop like a balloon, and everything inside, people included, would have actually ended up scattered on the moon. We never had that happen. So when the lunar module started to spiral back into the moon, it ended up taking a very shallow, high-speed orbit into the moon, and finally, it would strike something on the moon, literally almost horizontally at a slight angle, and just explode. Because the air would be, the hull would be breached. It would just go poof and explode like a balloon. And those scars are also on the moon. I've actually found them on here, and I don't have them bookmarked, so I'd have to go back and hunt them down again. I wouldn't bore you with that, but once I find them, I'll mark them, and then we'll actually come back, and you'll actually see the debris field that goes miles long on the moon. It's really, really impressive. Really impressive stuff. So I want to say hi to the other people that are here. I see Izabela's here. Hi, Izabela. Doomwalker, I said hi to you. It's good to see you, man. Gladys, it's, like I said, good to see you, too. You haven't been here for a while. Nice to see you. Donald Kunzer's with us. All right, good to see you as well. And like it, make sure you guys subscribe. It's free. And what do you get for that? Well, okay, I'll just show you real quick here. When you subscribe to us, what are you getting for it? Let's go there and I'll show you. This is skytourlive.org. This is our site. It's our portal to everything. Here's SkyTour live stream. This takes you to what you're seeing here, our live stream. Okay, the Patreon page is here. Okay, and if you want more, well, we have the SkyTour shop store on Etsy. You can contact us. We have SkyTour Radio, which is a Sunday night 2-hour astronomy show on KGRA Radio. And I'm an astronomer. That's what I got my degree in. All right, so this is what we look like. So when you want to talk about astronomy, when you want to talk about science, SkyTour Livestream is the place to go. It's STLS. Scrolling down, the real benefit is you can say, I want cool pictures. Okay, and what does that mean? Well, I'm a disembodied head. I'm usually against a black background. Every picture we take with our telescopes is saved and immediately sent up to a server. So we say, let's go to the online database. And I know this is bright, sorry. But when you get here, every one of these folders, scrolling, it just goes on and on. Okay, every one of these folders has our stuff in it. Now, I did a private stream for myself. I just did a couple of shots yesterday. I did the Beehive cluster last night, and I just checked it out. And this is the image that I captured. Okay, and this is up there. This image you can take, and it's yours if you want. Ta-da! You can take it. Look how beautiful. It's a beautiful cluster of stars. You can see some beautiful red giants in this cluster. And when we take these pictures, and I'm doing it with all of you, what I'll do is I will tell you the background of these clusters. I'll tell you about them from an astronomical point of view, from an astronomer's perspective, but at a level that everybody can understand. And that's the kind of thing which I think is really important, because what I want is for you all to join me in this quest. Now, you might have noticed Calabos in the chat. Well, Calabos is a very special SkyTour supporter. All right, there's a few of them, and Calabos has joined forces with us, and along with Tiffany, his counterpart in crime, and Calabos and Tiffany give away astronomical equipment, from telescopes to night vision systems, and we do it exclusively on our channel, and we're his outlet, we're his distribution point for this. So if you want to see this cluster, this beautiful cluster here, then you might win the binoculars that we'll give away on many of our streams. And if you don't know whether you won or not, or you had to go to bed before you could actually see it, well, if you came back here, you come down, you scroll down, telescope equipment giveaway winners, you'll see your name in here. You'll see who you are and what you won. And if you say, oh no, that's me, then what you do is you can contact us, okay? And so when you contact us, you go to contact us right there, and it'll take you to your email or what have you, and you can actually write to us if you want to, and say, hey, that was me. And if you want prints, you can go get prints, and these will be, you got to see this to believe it if you haven't, for those that haven't ever seen what we've done. This is a photo gallery that we have of objects we've taken, and it's just, these are beautiful. And the nice thing about these, as everyone here will attest to you, those who haven't seen it, these images don't take hours to acquire. Many times to get an image like you see here, this is the Orion Nebula with the Running Man Nebula, and then all this dark dust. This stuff is, the dark dust is where we come from. This is the stuff from which life is made, in those dark dust clouds in the universe. And so image like this might take, maybe you might have to take, say, 400 shots at 3 minutes apiece to get something like this, depending on your telescope setup. We have a very special system. In fact, our telescope is made by Meade, and it's the only one on Earth that's converted for Meade anyway, that allows us to see it 25 times faster than we have ever had a telescope do it. It's 25 times faster than all the other telescopes like it. So this photo was 25 seconds long, not hours. And so while you're sitting there watching, and I'm telling you about the Orion Nebula, you're literally watching what you see on the screen come in right in front of your eyes. Where do you get that? There's no one else doing that, you know? This is a beautiful one. It's called Casper the Friendly Ghost Nebula. Another one, this is called the Elephant's Trunk Nebula. This is the Messier 33 Galaxy. And these are all low res because they're on our website. But oh man, you should see them in high res. And where do you get that? By going here to our online server, which you're allowed to do. And look at how big this picture can get. These are large. Now, notice inside the middle of this cluster, that tiny thing right there. You know what that is? That's a galaxy. Millions of light years from us, but seen through the cluster. All right? So you learn about all these things. You see these many crazy astronomical discoveries. All right? And so we'll see galaxies in clusters. We'll see these beautiful stars. And we'll see many, many more things like this when we show you in our world of imagery. Okay, here's one I took last night too. This is called the Cosmic Bat. This is just the raw images. These aren't even the processed images that we've done. Okay, this is just a raw image, and you can see more dark dust and more of a nebula in here. This modeled stuff, that's noise, and we get rid of that. We get rid of that in the final versions. And for the Patreon members, they can see and get and keep the final versions of the images we take. So there's a lot going on. There's a lot that we do, and we teach you how to navigate into this stuff and navigate to find, all these other things that we're making. So we have literally hundreds and hundreds and hundreds of images out there. All right. So 20 days ago on the 28th, we did the 37 cluster, the double cluster, the Fishhead, and all these things here. Okay, we did the Horsehead Nebula. Okay, the Horsehead is in Orion. And look at this beautiful nebula. Look at that. Isn't that beautiful? That is something else. Now, there's halos around the stars because our telescope is, again, 25 times faster. So it's actually pretty crazy. And you can see this beautiful nebula. It's got a star there. It's got a star there. A star in the nose. Then you got this area over here. Beautiful. These are emission nebula, the red ones. These blue things are called reflection nebulae. Okay. So if you think this is kind of a commercial for SkyTour Livestream, I guess it is. Because joining us is free. Seeing these kinds of things, taking images like this very one, free. You can have this image. It's yours to keep. Download it. Make it your background on your machine. No worries. All right. And if you want it on a bed sheet or a blanket, if you want it on sneakers, I have a pair of sneakers with our objects on it. In fact, the Horsehead's on a pair of sneakers I have. So we have about 50 products that we've made with all these different things on it. And they make great Christmas gifts and birthday gifts. And people who love astronomy, man, they just buy and buy and buy. They love them. There's the Andromeda Galaxy. That's 2.5 million light years away. And it's heading right for us. No lie, it's actually going to collide with us in a few billion years. And it'll go through us. And we'll get absorbed into it. And our galaxy's probably going to get ripped apart. Our galaxy has about 100 billion stars at the low end, maybe 400 billion stars at the high end. We can't see beyond the center to count the other side. But this galaxy has over 1 trillion stars, a lot more mass. So we're going to be the unlucky edible for the Andromeda Galaxy because they'll just take us and probably fry us. And then out in the desert, this is actually our observatory. This is the one out in Arizona. This is Sky Tour West, number 1. And we have Sky Tour West number 2 going in out there. In fact, next month I'm going out there to look at the next site. And then we're putting Sky Tour East back up. We had Sky Tour East here first for the very beginning. And I'm in Connecticut, and I run this telescope here out in Arizona, which is 2,500 miles away from here. And I do all that. See, tonight we're not able to do it only because of the fact that it's still windy. Windy. It's still got a lot of clouds out there. So as it stands, I think that this is sort of a great compromise to do a cloudy night stream. We're going to do more of these too. This is a series of teaching streams too, to help you learn all about what we do. Okay, but skytourlive.org. Skytour live stream is the stream. It's free. Join us. Patreon page. We could use your help. We always can. And if you want to see and listen to our radio show, you can go to Skytour Radio. You can contact us. You can go buy some cool stuff. That's the Helix Nebula. That's one of those planetary nebulas I was talking about. That star in the middle there, that blue thing, that's a white dwarf. That star, okay, is only about the size of the planet Earth, okay? However, it's hundreds of light years away, and we can still see it as a blue dot. That's because it's so bright, and it's only the size of the Earth, all right? This stuff was all cast off from it. It's the former atmosphere of the star blown off as the star began to, and it was a slow motion process. As the star began to die, basically, it sloughed off its outer layers little by little, and then it went into these what are called thermal pulses, where it pulses, a little comes off, pulses, a little comes off. One pulse was particularly pronounced. You can see this ring out here. There's a little more on that side, and so that's what happened. You know, and because it's blue, it means it's extremely hot. This star in the middle, the remains of what was the star that created this Helix Nebula, is this white dwarf, extremely hot. And in the universe, hottest means bluest. And so blue is the hottest color. White is the next thing. You think white hot is the hottest. It's not. Blue hot is. When you look in a flame, say you're running a burner or a torch, you run the torch, and you'll see that the very cone of the flame is blue. That's the hottest area. And then it gets lighter, and then turns orange, and then red. And that gets progressively cooler. Okay? These gases here, the green is oxygen that's ionized because of this white dwarf. It's taking the oxygen atoms and popping the electrons off of it and making it get ionized, but the electrons can rejoin, and as they do, they give off light. Oxygen gives off a characteristic green. Hydrogen out here gives off a characteristic red, okay? And so you're seeing that here. So every image has a story. Every image has a genesis to it, and we love to tell you about that. This is the telescope that Calabos and Tiffany gave away to JSCO 77. He was our first one on 1220. Mind Remote 7 won Celestron binoculars on 1228. And on 1/7, the Goblin won a pair of Celestron binoculars. And Mike and Tiffany and Marianne Robb and I had a meeting last night. Tara, who is the other officer in our nonprofit Sky Tour livestream, couldn't join us that night. And we talked about the process of what we're going to do. So that's, we have processes. We're working on possibly different levels of binoculars for people. Okay. Gladys says, wow, they gave a telescope too. Yeah, that's right. We did. Okay. Thanks to Calabos and Tiffany. That's the telescope that JSCO 77 won. Okay. And I think that it'd be pretty cool if, more of you participated in our online contest. It happens during the streams. And in the case of the Goblin, here and these other winners here, the actual contest was think of a number between 1 and 1,000. You get one guess. You put it in the chat. Goblin guessed 888. And it turned out that was the exact number. So if someone gets the exact number, contest is over and they win immediately. Okay, but if we don't stop the contest, it means that there's still a chance for you to win. And so far, only one contest was stopped like that. We didn't even stop it because we only worked this out last night. But so we have 3 winners so far, and there's many, many, many more telescopes, binoculars, and to one of our Patreon users, if you become a Patreon member for 6 months at the lowest level, even, then what you can get is you can get yourself if you win, a night vision system called the Aurora Sport. All right, and I have one that I bought myself, and it's a beautiful color night vision system. And you can buy it if you want to go spend $400 or $500. But when we do this for our Patreon subscribers, we're going to give it away. So you might want to consider it. I think we have a tier at $3. So if you join us for a $3 tier and you're in it for 6 months, you become eligible in the contest. And so we'll actually run the contest among our Patreon subscribers. That's higher end equipment, and it does require more of a commitment, But we're very interested in this. I see Daryl's with us. Hey, Daryl. Yeah, sorry, Daryl's usually my cohort in crime here. And I just figured that I was doing this on the spur of the moment. I figured I would get into it. I didn't even give Calabos and Marianne any warning. I just went and did it. I didn't even tell Daryl I was doing it. Sorry about that, Daryl. But since we're not using the telescope tonight, I figured I would just do the lunar stuff. But there it is. So that's here. This is skytourlive.org or skytourlive.com. We have both portal sites. But join us and hang out with us and see what the universe really looks like through the eyes of a most amazing instrument on the planet. All right. So back now to the moon. And here we are. We're still at Apollo 16 or Apollo... it's Apollo 16? Is that where we are? It's Apollo 16's landing site. And we talked about the distance to the distant mountains and how it looks. And as we zoom out, you can see why it would be difficult to see these objects on the moon. Because even with a very powerful, extremely powerful telescope, we can't see close enough. Down here, we'd have to zoom way in, okay? And you might think, well, at this level we can see it. No, we can't. All right, we'd never be able to see anything at this level. Look how much further we have to go in. We have to go further and further and further until finally, when we get to like this level, now we can just start to get a hint of something here. And you literally have to be just a few miles above the moon to see it this way, like 60 miles above the moon. You don't have the ability, we don't have the ability to see the moon with that high resolution up close. Even the Hubble Space Telescope couldn't do it, because I actually did an analysis of the Hubble Space Telescope on the moon and why it doesn't show things that are really cool. And that's because the Hubble Space Telescope has a certain number of pixels in its array, okay? And you would have, if you got down as close as you could, if you could see as close as you could with the Hubble Space Telescope, the entire landing site for, say, Apollo 12 or Apollo 16 or even Apollo 11 would be within 1 pixel of the camera, okay? It's designed to look far away at great large objects, not at tiny objects relatively close to it. So I think that's pretty cool. Now, I see the chat people are asking about things in the chat. Let's see if I missed something. All right, Daryl's cool. Well, thanks, Daryl. Anahata, hey, that's Bonnie. Anahata 77. Cosmic Ray is here. Yep. Not bad. I'm just reading up. Gladys says, I hope it goes to someone who finds a new discovery, not me. Well, how do you know you won't be the one? You know, now here's the thing. We decided with Calibos that maybe giving away telescopes is great, but most people, if you give them binoculars, they can go outside and look up at that fuzzy thing and immediately know what it is by putting the binoculars up. It opens up the universe to you, and that's what we're all about, opening up the universe to you. This is an example by doing this QuickMap analysis with you to show you what's going on. You can get 3D prints from here. Let me show you another little cool feature. Let's go down to Copernicus Crater down here. Okay. And again, Copernicus, you can zoom in, and then you'll see the data change to the higher resolution data as we get closer. All right. And you can see an amazing amount of detail. And then as we get closer, you can start to see the little boulders on the surface. Look at this rubble pile right here. Look at this. Check that out. Right? Isn't that cool? There's one there too. So you say, well, wait a minute. Why would there be rubble piles on top of the hills? Is it on top of the hills? It could be, right? So this is what this crater looks like from down low. Look at that. This is an extremely rugged terrain. I don't think anyone would want to spend time here, you know. And this is actually one of the reasons why we didn't land here, okay, with the lander. Okay, now if you want to know what it looks like here, you can, again, you come back to this magnifying glass and grab the line and say, well, what about this right here? What if we cross this? See how the line changes? And then you see the actual line that's going on here. So up this hill at the end here, all right, you can see right there is the hill, right there coming over the top of the hill. Here's the peak of the hill right there. And we look at that and you say, wow, look at that. There's actually a boulder pile on top of that hill, and it comes right down here. Many of these craters, you can see that a lot of the rubble has rolled down the hill and left a trail. Now, that could have happened billions of years ago. There's no erosion at all on the moon. So with no erosion, then anything that happens to the moon will stay that way forever and ever and ever, unless something massive hits the moon. Okay, so that's how that works. It's pretty cool. All right, so let's pop out of here. And once again, just to show you, let's suppose you want to do a 3D print of Copernicus Crater. You zoom out, take our delimiter here, click once, click twice, click a third time, click a fourth time, and then finish out the square, blue outline. And at this end, you double click. And there you go. So now you have Copernicus Crater selected right there. And remember what we talked about? We could either look at the feature info, it tells us how many square kilometers this is. This is 24,716 .440 square kilometers in here in actuality. We can inspect and see all the different things. These are all the different data that are available inside this square, the yellow square indicating that that's where all the data is. And then if we go to other, we go to 3D printing again, and we can look at and make a beautiful 3D printed model of Copernicus Crater. And there it is. And we say export 3D model, and there's our model. And I have a vertical exaggeration of 1, and you maybe go to 2 just to be more dramatic. But then what you do is you give it a nickname, and you say build the 3D model. Okay, so this will be Copernicus. Oh, sorry, I already had it. And then you say build your 3D model. And after you build it, you'll have a download link And that download link right there, will give you a zip file within which is an STL, which is something you can send to any 3D printer and print out the crater on the moon. We do this actually, and we're going to do, among things for people that may not do 3D printing, we will offer 3D printed moon models as well, as part of the contest as well. So you'll see that we may be doing a contest for a Copernicus crater, or a contest for a whole 3D printed moon, which I do have here. I made a beautiful little moon, and it's a beautiful round moon. You can see every crater on it because we have a really good 3D printer, and so it came out really pretty. So it's all good, and everything we do is so that you guys can further your science, further the cause and your understanding of the universe. It's all about you, and so I like doing all this stuff for you guys. Daryl does too. Izabela enjoys working with us and helping us out. Calabos and Tiffany do. Marianne and Tara, we're committed to you guys. We really are. And so we often will do things like this stream where it's actually not clear out there right now. So what I'll do is, just to show you that, I'm going to go to our weather report here, and we're going to head out into the desert, and let's see what it looks like out there. Yeah. So right now, here's the observatory, and here is the cloud banks that are currently passing over the observatory. And this is the only reason that we're not going live tonight with the telescope. So I think that's unfortunate, but that's okay, because you got to learn about the QuickMap. So let's go and summarize a little bit more here so you guys can see. I think that it's very important to make sure you understand all these things. Let's go back to the overlays. All right, we're going to turn off the landing sites, the anthropogenic or human-made features. All right, and let's look at something else. Let's get out of here. Okay, and now what's interesting is you want to see like geological features and maps. Okay, you can look up pit locations. Okay, where are there pits where there are geological pits on the moon? Now, pits aren't craters, okay? Pits are actually volcanic areas where there was a pit, a subduction, and so we can also look at craters that are 5 to 20 kilometers in size, or well, I mean, everywhere. I mean, there's just so many things you can look at here. So it's really incredible how many different things we can do on the moon and how many different things we can see. All right. And so we'll see all that data come out, all right, once we select it and move through it. All right. So right now, we're seeing that, okay, in this case, we have global light planes, all right? And if we zoom in, well, yeah, by golly, look at that. You see these lighter planes. That indicates that they are made of a different type of material that could correspond to a different age. It could correspond to a different material altogether, all right? And so you got to give it time to come in. It takes time for some of these things to come in. But let's, we'll click on pit locations, and then when this one comes in, it's going through, you have to understand, it's going through millions and millions of data locations. And it's trying to show them to us, all right? And it says, okay, this page is slowing down Firefox. Yeah, it sure is, okay? Because it's taking time because there's so many of them. So I'm gonna stop this right here. So there's so many things that are happening on the moon, and so many science missions that have gone to the moon. After all, it's our biggest neighbor. So we see all these things. It's very exciting to see them, and we expect to see all these amazing spots. Here's some more pits. Let's go in here and dig in and see what this shows us. All right, so you can see what I'm talking about when we talk about pits. Okay, this is Aristarchus crater. All right, as we zoom in, you can see, okay, that there is a pit. These pits are different from craters, right? These are volcanic in origin, or they're this isn't a crater. This is a pit, right? And it looks like it's. You look inside and you say, "Oh man, it's dark in there." Okay, well, it's actually just a pit brought about by the volcanic origin. Like for instance, after craters formed, this crater here that we're looking at is a crater known as a complex crater. It actually has a walls around it and a central peak. How does that happen, by the way? When you look at a crater, we have simple craters, which are just little bowls. Okay, this is a bowl right here. That's a simple crater. This one is a simple crater. This is a simple one. They're just rounded bottoms, like a classic crater, right? But a complex crater is different. When a projectile strikes the moon, it hits with such force that, first of all, the projectile is vaporized, right? And that energy of motion is converted into heat. And what happens is the entire ground here from the impact through, now the object might only have been about this big, okay? But it may have struck with such force that it literally spread out these shock waves all the way out. And for a moment, although it was also causing areas in here to get molten and melt, okay, it also was causing things to happen like liquefaction, where it creates such vibration and shock to the soil that for a moment the soil acts like a liquid. Okay, you've seen this in the Marina District in I think San Francisco during an earthquake. Houses just sunk vertically into the ground. Like, what? How could that happen? Because of the fact that they actually ended up getting in a liquefaction zone where the soil was vibrating such that it acted like a liquid and the houses basically sunk. Right? Well, in the same way, liquefaction acting like a liquid caused these central peaks at a massive scale. So how's that work? Well, it hits, right? The stuff is displaced and it acts like a liquid, so it comes out and then it comes back in. And then that stuff, when it hits from all sides, it comes in as it comes back in, and then it makes like a bloop. It's a splash, right? And that central bloop is that central peak, right? Frozen in time for billions upon billions of years to come, right? So these central peaks are formed through the impact process, and it takes a certain size meteor, a certain amount of energy expended to have that happen. The other thing that happens with these complex craters is we get these terraces. You see these rings like this. Some of them are very, very sharply defined, okay, like in Copernicus Crater, okay, and some of them are less sharply defined, okay. Let's see. Let's go find one this one looks like it has it. Okay, here's a crater that has just a couple terraces, all right? Again, this is, the same kind of problem we see all the time, and that is that, the energy and the size of the impactor make all the difference. Yet over here, this is actually a simple crater. This isn't a complex crater. Look at this one. See that? It's just a bowl. It's just a bowl-shaped crater. It goes right down and right up. Now, what's neat about these craters is sometimes if you look in these, you'll find a track where a boulder got loose from an impact somewhere else and just rolled down into the middle. Okay? And you can see that there's debris on the bottom here. this stuff came down to the bottom at some point, and this is how much stuff filled it in over the billions of years intervening. So that's what's fun about looking at these craters. They're little flat bottoms, and now if you look at this, you say, well, I want to compare this crater to this crater. This crater looks like it's as deep as that crater. Is it? Let's find out. You go to your magnifying glass tool, pick the line, and draw a line. So click once, draw a line through, and then double click and check it out. All right. So we'll go inspect, and we look and see, no, not at all. That crater is actually, if you look at that little area right here, this value down here underneath the red, okay, it says minus 2581, and then this crater is much deeper at minus 3395. See that? So this dispels the myth that all craters are the same depth. Okay, and these are both simple craters, right? Not complex craters, right? And the simple craters, as I said, usually have debris that's slumped down and filled the bottoms. Pretty cool, huh? There's a complex crater. All right. Now let's take a look here. This crater, this bigger one, is minus 3397. Let's draw another line through this crater and see how far this one goes. Now it's got a central peak. But let's see what happens. Okay, so here, this one is minus 4139 in its bottom. Then there's the peak, and the other bottom, minus 4116. So it's actually deeper than the simple crater, as expected. So the bigger the impactor, the deeper it can plow into the moon. It kind of makes logical sense. So this shows us then where we have our lines. It's really cool. Now, so you see that this stuff is used. You can see that this stuff is used to actually do some really cool science. Now, here's something you don't get to see often. Right? Look at this. Now, at first glance, you might say, oh, that's just a line of craters. Actually, it's not. Because if you look, it continues here. See that? And continues here. And continues here, all the way down. What are we looking at? This is a lava tube. This is an example of where we would love to set up a base inside a lava tube. As we get closer, you notice these are like pits, little pits, okay, on the moon. See that? And the 3D model shows it best. And they're actually pretty big when you get down to it. And what's underneath them is a lava tube. There's the rest of the tube is here, not collapsed. Here the roof has collapsed in this cavern of the lava tube and allowed the above the roof to collapse into the lava tube, and we're seeing that right here. So when we see chains like this, these pit chains. These are chains of collapsed lava tube, and here again, as I said, there's still a lava tube under here yet to collapse. It hasn't collapsed yet. Now, what could cause it to collapse? Well, we don't know. Maybe the impact at this crater caused this to collapse, like boom, and then boom, this collapsed out to a certain distance where the shock wave got lessened, perhaps. Don't know. Okay, so inspecting the moon gives you so much incredible information, and you learn a lot of geology by looking at the moon, right? Like lava rills. Okay, you see areas where lava stopped flowing, and it made like a rill. And if we actually do our measurement again from, say, here and go here, now let's take a look at what that looks like. You'll see it's amazing. it starts here, right? So all the way out here, it's relatively flat. It goes a little deeper, and then bam, it shoots way up, right? It shoots way up right here. That is actually, it's shooting up on this location here. You just see it as a subtle change in the color, but in reality, you're going from minus 2512 to all the way to minus 2279. So you're coming up hundreds of feet just to go here. And in this mode, you can actually go in there and say, well, what's that look like if you get down close to it? Oh, there's what it looks like. Check it out. That's neat, right? So you can actually zoom in on it and then do your 3D view here and see how it looks in real life. That's kind of cool. It gives you an interactive methodology with the moon that we just haven't had before. Okay, so we got our measurement tools. That's what these are. You can keep doing them all you want, you know. And then and they have settings too. There's settings like show gradical. We can actually show lines in the moon so you know where you are at all times with latitude and longitude on the moon. Okay, so we can do that. We can actually say enable terrain. If we don't enable terrain, then it's all going to be flat. You don't want that. So you're going to want that. Okay. And so you can also, if you wanted to, you could actually turn or use an area of the moon and photograph it and download it. And by doing that, what it'll allow you to do is it'll allow you to actually spend time trying to look at the real moon with a telescope and seeing the things you did in here. See what you got for resolution. So it's not bad at all. It's pretty cool. We still have clouds out there right now, and it looks like we're going to have them for some time, which is no fun. Okay, so let's go back to the LRO QuickMap here. Okay, so again, this is what you're met with, and you have this left side column you want to go to, and I like to go to the Lunar Globe because that allows you to do all these really neat rummaging around in craters. Like here's Copernicus Crater, and how do we know that? Who would knows? You go into the layers, and you go into overlays, and in this case, nomenclature. Okay, and nomenclature tells us that that's Copernicus Crater. And so if we go in here now, if we zoom way into Copernicus, did you ever wonder what it would look like from inside Copernicus Crater? Let's go in. We're going to drop right in here. Okay, here we are. We're inside Copernicus. We're down there as pretty much as far as we can go. All right, and then what we're going to do is look around. So now from inside Copernicus Crater, this is what we see. That's pretty cool. And now on the right side, a cool thing is this guy right here. This is a orbit. It's an orbit tool which allows us to orbit whatever object we select. Okay, and pick an orbit. So this is something that you might want to do as well when you start to look around Copernicus, right? Okay. But, so, Copernicus, again, complex crater, made through that liquefaction process I told you about. It has multiple central peaks, multiple bloops, okay? And you can see multiple terraces, all right? Really interesting. These are scarps over here. These are actually pretty steep, and if you look at them, you can see that that's pretty steep. This is not exaggerated. This is how it is. That's quite an angle going down, you know. And so, you know, we could set up an entire moon base right here. Right in Copernicus Crater, right on this spot. Right there. We could set it up. And what would our world look like? Well, we'd have the wall behind us. And if we come around this way, okay, and look this way, we would actually have the entire Copernicus Crater spread out before us, but we'd have to get up higher to see it. See that? Sorry. I'm in the wall. So that's cool. And if you want to know how to do any of this stuff, again, this is the LRO QuickMap. It's real easy. You know, you guys can have a blast with this. Now let's just do something for fun here. Let's go to the other side of the moon. Right? And to do that, of course, all we have to do is spin the moon. Right? And the data comes in very quickly. Right? And as we spin through here, this is the crater Manilus. That's pretty cool. But you see there's a lot of these volcanic pits here. Like here's another, this is another lava tube array. And Hyginus is another area where there's been a collapse in the roof of the lava tube. That's where you got these pits in. Okay? There's a lot of lava tubes on the moon. There really is. And so we see that here as well. Another collapse. All right? Now, I know that looks weird to you. Some people see this as bumps. But again, spin it around, and they'll look like pits. It's an illusion caused by your brain. Now it looks like pits. Okay? Go this way, and because your brain expects the sun to be on a certain side, you may not see it as pits. Most people now see this as pits because we already saw it that way. Okay, so as I said, we're going to go to the other side of the moon. All right, so we'll zoom out and check it out. All right, and there's Mare Tranquillitatis. That's where Apollo 11 landed, the very first one. So as we go over here, here's Mare Nubium. I'm going to show you another really cool crater on the way that we really think is the coolest thing. Okay, there's Copernicus, but let's go this way now, and I'll show you. I think it's right down here. Let me get more overhead here. There we go. All right, so I was looking at it just a little while ago when I came in here. Oh, wait a minute. I am rotated. I gotta get back to where we have to be here. Let me rotate us back. There we go. And now we come over here, and it's really, it's right nearby here. Where is it? I just looked at it. I'll find it. It's right on the edge as seen by us here. Alright, I'm getting there. Hold on. I'm trying to get back to where I was. Let me back out. Oh, okay. I get so caught up that I missed it. Okay, so it's over here. Let's go down here. Over here. Let's see. See that even an astronomer can get confused about the moon sometimes. I'm looking for one particular object that oh, there it is. I see it now. I didn't go far enough. Okay, here is an example of a crater that is fascinating because it's not just one crater, it's two. It's called Messier. Now you may know Messier as Charles Messier, the father of our famous Messier catalog, but he's had a crater named after him. It's called Messier. Check this out. Messier's weird. Most craters are round, aren't they? These are oval. What happened there? What happened there? Good night, Bonnie. Yeah, what happened there? You know? Hey, Vincent, how are you? Good to see you. Okay, well, I'll tell you what happened there. Okay, there are different impact speeds that meteors can have when they strike the moon. Some of them are low impact speed, and some of them are high. And some of them are shallow angles, and some of them are high angle. This was a shallow angle impact, and look at the rays coming out from here. The rays are going some distance away. Now you might say, well, how far away? You know the answer. You come over to your magnifying glass, click it, grab a line, click on Messier in the middle, and click out here to the extent of the rays. And you can see that this ray went 159 kilometers away from Messier. How could it go so far? It could go that far because the moon is 1/6 of our gravity. And because it's 1/6 of our gravity, it means that we have things on the moon, once they're thrown up around the moon into the space around the moon, they will continue to keep moving. So in the case of Messier, there is a ray structure that is actually quite extensive, and that's really cool, you know. So now if we dive down into Messier, let's turn off the nomenclature for now because we know what we're looking at, right? So we turn off these. All right, so here, what's it look like? Well, look at that. Now we see how this looks. This is one crater, and it's theorized that the way Messier formed was there were two objects moving with each other, moving together, and they struck the moon at a very, very low speed for whatever reason and made these oblong craters, still fast enough to vaporize themselves, but not fast enough to spread the energy in all directions equally. Now, how does that work? Well, if you go to a pond and you take a nice flat rock and you fling it level across the pond at a low trajectory, you can skip it across the pond. Do you get any oval splashes? No, you don't. Except at the very end, where when it hits at the very end, it'll go round splash, round splash, round splash, dragged out oval splash, as the energy is reduced in the system, right, with the rock. So at the end, you'll get this little oval splash. And what we're seeing here is that point in time where this object that struck the moon was of a low enough energy, comparable to that end splash of a skipping stone, that it made an oblate oval crater. The craters that are round, right, could have been low impacts or high impacts, and you'd still get a round crater because they had high energy. And the high energy is represented, for instance, when you're skipping the stone across the water, and in the middle of that skip is hitting skip, 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 skip. Every one of those skip points are concentric perfect circles moving away from where the rock hit. That's because the energy distribution is spherical or circular around the impact point. So it goes out the same way in all directions. When it gets low energy, you might get a dragged out oval, and that's what we're seeing here, right? Hopefully that makes sense to you. Now, again, you can ask questions and say, well, I want to know what it's like if I was inside this crater. Well, you can come right down in it. You're going to see lots of debris. And what you can do is use your middle mouse button. That's what we use to actually hit this, right? You do the middle mouse, and then you do that. Okay, and now we can look around from inside the crater at the walls around us. Look at that. Isn't that crazy? And we pull out a little bit, and we can see the other end of the crater there. That's pretty cool. No, that's crazy. You're inside one crater inside the moon. Now you say, well, wait, one crater. How big is that crater? And by now, you know how to do that. You come over to your magnifying glass. You go grab the line, click on one side of the crater, click on the other end of the crater, and then you double click at the end. And now it will draw out the path for you. And then as you move your cursor, you bring your cursor to the upper right there, over there, and you move it to the left and right. But inside the crater is actually an indicator. As you move your mouse through, you actually watch where it moves. It tells you exactly what the depth is at that point, right? And if you want to know how big it is, well, the length of the overall line is 15.3 kilometers. Okay, 15.3 kilometers. That's pretty big, right? All right, so that's cool. Yeah. And that line, by the way, that 15.3 kilometers is not from here down the slope, down the bottom, up there. It's this straight across number. Okay. So that's what you're seeing. So that's cool. So that's neat, and it kind of gives you the profile of the crater and everything. All right. Neat stuff. So we just inspected Messier Crater on the moon, and we learned a lot about it. We learned about it was a slow impact. It was a very, very shallow impact. Low energy. Think of the skipping stones. High energy makes concentric circles in every one of those splashes, but at the end, the rock can sort of ride along and make an oval, make a long splash, and drag out the splash. Now, in terms of the moon, low energy still means an impact that will vaporize the impactor, but it's actually lower energy with regards to the rock strata around it. And the rock strata is a lot harder to make into a circular impact feature than water is. So it's up obviously many notches. Here is a simple crater, okay? And again, here's a simple crater. Let's see if we can see any trails on the wall of the crater. Usually, when you look in the walls of the crater, you can see maybe a boulder that's rolled down, and it will have a very specific trail. There's many like this, so you zoom way in, you can see them. Okay, and you might see things like this. That right there, that's an artifact where the data wasn't quite complete, and it got a little bit stretched. Oh, there we go. Look at that. Here we are. Check it out. This boulder slid down the wall. You can see it right there. See the trail? See? Really cool. So, and where did it slide to? Well, it's sliding down into the crater down here. So, what would make it slide? Well, some kind of impact elsewhere on the moon is probably why this boulder began to slide. And that's what we're seeing here. This sliding process that we'll see, and we'll see the trails. If it gets tumbling, then it could leave a path that's thousands of feet long. Really cool. So inspecting and looking for boulders that are rolling into the crater is really interesting to do. And again, you could do it like this and say, well, that's a pretty steep slope that we're on right now. So once something starts rolling, it's going to keep going. You know? So that's what I like about these simple craters. You can actually identify the rollers. So I think that's pretty cool. Izabela, thank you for putting up the Patreon. That's really kind. So this is the kind of stuff we do. And here's another simple crater. We can go crater diving again. And we get our data. And now let's go see if we can see if there was another roller in this crater somewhere. There might have been. Just move around and look. All right, well, I don't see any in this crater. We saw one in the previous crater just now. But then again, there's several million craters on the moon, so we have a good chance of finding more. So that's what's neat. And I'm going to show you another location which is really cool. And this is one we've 3D printed for people before because they think it's really neat, and it is. Let's zoom out. There's Messier again. We're going to go to the dark side. Let's go over to the dark side of the moon. Remember Pink Floyd? There is no dark side of the moon, really. As a matter of fact, it's all dark. Right? There's Mare Moscoviense right there. That's one of the only seas that is lava fields on the far side that is from flood lava that's flooded the surface. But here's the one I wanted to show you. This is Tsiolkovsky Crater. It's right at the limb of the moon as seen from us. It's kind of on the far side. You really can't see it too well. But here's what's neat about this. You can see that the impact that created it flooded the base of this crater with lava. So this central peak was probably deeper in here, and you can see how you could excavate out this dark gray lava and get back to the original crater that's underneath it. It's like, if you think of it as like water, okay? But if we zoom in on this, okay, you can see some really interesting features at the border. Now, you'll also notice that there's no spot on the moon that is free of craters. So this tells you chronology. This is a very important thing, chronology. When this crater was made, all right, none of these other craters that you see in here were made. This was all a pristine lava field here, a mare, we call it a sea of darker material. And these craters, all of them, look, the farther we zoom, the more craters you see. These craters were not there, all right? These came after. And we learn a lot about the chronology of impacts through these studying the craters and the mares, the seas, and the overlying things that happened on them. Very, very important. So if we look at the peak here, at this central peak, you can see that the central peak is very chaotic. You know, again, this is the bloop, you know, that frozen time, all right? It's very chaotic, and you zoom in, you can actually see these amazing features, including what we've been looking for. Look at these rollers. These boulders went rolling down the slope here, all right? Here's one. Look at this. It rolled down the slope and kind of went in a wacky zigzag pattern for a bit, all right? And there's many such rollers in here. Many objects came rolling down the slope here and then stopped, you know? So this is what's neat when you can spend time on the moon looking for all these things. This is another, okay, here's one, but now look at this. Here's another one right here. A very chaotic, this one looks like it went flop, 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 and just flopped over several times. Thud, 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 thud. And again, we might be able to do this. We might be able to take our, if we're not too close to the limit on this, we can take our thing here. Okay, this is a 57 meter long. You can see it right there on the label. But if you double click, it'll show it again. It shows it's 0.054 kilometers. And of course, there's 1,000 meters in a kilometer. So you can see that this here is a 57 or 54 meter object here. Really amazing. All right. 54 meters. Think about that. Okay. It's like a 160, 170 foot long giant boulder flopping down the side here. Now, this one did too. It came from a higher distance, and as you can see, it went airborne. Right, this one, right here, went airborne. It came down. It got enough speed, so it went bang, airborne, bang, airborne, bang, 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 until it came to rest right here. See that? You learn an awful lot about this from looking at these things. And in the Moon 3D, you can look around here and get your bearings. It's really the coolest thing. So hopefully you're enjoying this. I don't know if, Doomwalker 42. That boulder is actually my last brain cell on a Monday morning. That's actually funny. You're not the only one. There's other people like that too, Doomwalker. So yeah, so you can see that the moon is not just never ending, right? Or sorry, the moon is not just static. Things are happening on the moon. Izabela asks a question, I think. Calibos first. Marc, is it possible that these moon boulders move because of an impactor, or are there moonquakes? Actually, both. Okay, the moon is tectonically dead, as far as we know. All right, but we've had surprising things happen on the moon. We've seen some what look like volcanic outgassing that's occurred on the moon. So we're not quite sure how that happened. Maybe there's pockets of molten material in the moon that we don't know about. The possibility that there are moonquakes is a possibility. But you got to keep in mind there's no tectonic plates on the moon. They're not plates rubbing against each other like on Earth, where we'd get an earthquake or a comparable one on the moon called a moonquake. So there's no tectonic activity there like that. However, if something impacts the moon, like way out here somewhere or way outside this crater, look how far out we're going. Okay, so say this crater occurred right here. It's going to send shockwaves through the moon. Okay, they will dissipate over time. But maybe those shockwaves were enough to dislodge a giant boulder and cause it to go riding down the slope like we saw in here. Okay, like right here. And then a boulder would get sent down. Bam, bam, bam. Pretty cool. Now Izabela asks a question. She says, can we see the meteor or the crater of the meteor that hit the moon and was captured live? And yes, I'm looking for that crater. Okay, let me explain. On one of our streams during a January of 2019, we were streaming live a lunar eclipse. We had 5,000 people watching, and as we streamed, one corner of the moon, a little tiny lower left corner at the height of the eclipse, the moon was orange, we saw a white flash. We learned later that was a meteor strike that we captured. We were only one of 6 groups on the whole planet. Okay, Doomwalker says, I remember that. Okay, we're only one of 6 groups on the whole planet who actually caught it. And so that kind of put us in the record books, so to speak. And so that crater would be visible from the Lunar Reconnaissance Orbiter. And I will look that up. I'll find out where it is, and we will go see it. That's really cool. Let me actually... Well, while we're here, let's try that. I don't know. Where is the crater impact from January of 2019? Impact. Let's see if that gets us enough. Here it is. A meteorite strike during the moon eclipse. Let's see if this gives us the data we want. Yeah, okay, let's see if... I need latitude and longitude. Yeah, that's it. That's what we saw. But it doesn't tell us when or where. Oh, I'm looking. Okay, hold on. A flash south of the crater Burgu on the western part of the moon. Yeah, okay. Yeah, well, yeah, we do have meteorites hitting the moon all the time. Okay. Crater Burgu. Well, let's go see if we can find Burgu. And it was just south of the crater Burgu. It's going to be a relatively recent crater. We'd be able to see it. So let's go back and see if we can find. I don't know if Burgu is. I don't know if Burgu is going to be labeled. I think it will. We'll find out. don't know if we can name, or I don't know if we can actually search for a specific crater on the moon. We can filter by type, filter by name. Hey, let's try that. So, Bergu crater. Bergius. Did I mistake that? Did I not see it? Bergu. No, it says Bergu. They could have got it wrong. So let's go back to this. And let's say Bergius. Okay. So there we are. Let's see where it is on the moon and make sure that it's in the right location. Okay, that's the western limb. That's the Aitken Basin on the far side. And this is the near side. This is about where it was. So I think that Bergu, see if you look them up by name, and then you click on it, it takes you right to it. So there's Bergius. So south of it would be in this region, and it's going to be a tiny crater. It's only a few feet across. It might fall well within the limits of our view here, but you can see that depending on how well we do, we might be able to see it. Like if it's, see, like a crater like this, that right there is a new crater relative to these. Notice how it's sharply defined, and these are kind of rounded over and all these little things. That's a sharply defined crater. How big is it? Well, let's find out. Let's go and grab our little thingy here and touch it and drag it out. Okay, this says 55.94 meters is how big this is. So 55.94 meters is the size of that crater, and I think that might be too big for this one, but that is a relatively recent crater without a doubt. Okay, you can tell, like as I said, because they have this very bright reflectivity feature, and they're sharply defined. Pretty cool. All right, so as we zoom out here, but you see how well this works, guys? You just look it up, and you go back to your tool here, okay, your layers, nomenclature, and you basically search by name. Okay, and that's pretty cool. That's how that works. And so that's pretty nice. So once we know the exact location, Izabela, we will definitely find it. Doom Walker says, do you have a favorite crater? I do. I do. Would you like me to tell you what it is? Okay. Here, we'll do this. I'll show you. Know what it's going to be yet? Yeah, you do. Clavius. Click on Clavius. Let's go see it. There's Clavius Crater. Clavius Crater is a really interesting crater. It's actually just near Tycho. If we zoom out a little bit, you'll see Tycho right here. Tycho is a crater that has the massive rays on the moon that everybody sees. Okay? And you're used to seeing Tycho's ray structure going hundreds of miles. So that was probably a direct impact and just a lot of energy released. No, now you know Clavius. Dumarcus says Tycho's the only crater I know by name. There's Tycho there, right? Up here, the other big one here, the big splashy one, that's Copernicus. Okay, and down below Tycho, then you have this guy. This is Clavius. Clavius is a really interesting crater because if we zoom in on it, okay, it'll get better. Okay, as we zoom in, you'll notice that it has these secondary craters inside of it. What's interesting is this crater was made first. This was a pristine crater with nothing in it, okay? And then subsequent impacts created all these other craters inside of it. One hit here, destroying the wall of the crater, right? And then once again, we talk about those volcanic zones of collapse. Well, we see them. Here's more of these volcanic pits, these collapses of the lava tubes here. You see them right here. Okay, now sometimes the data makes it a little tricky to see, right? But that's what they look like right there. There are the pits. You can see that they're collapsed. Now, why are lava tubes so good? Lava tubes are exceptionally well suited for a base because of the fact that inside the moon, if we could get into a lava tube, it's a hollowed cavity already made, and it protects us with what's inside. It'll protect us from the ultraviolet energy of the sun, which is sterilizing and could kill us. And so if we don't want to have to protect ourselves from that, we just put ourselves inside a lava tube. That's the idea. Hey, Fantasy is with us. Fantasy's with us. You know? So, that said, my favorite crater is Clavius. Now, why else? Well, a few reasons. Number one, Clavius is the crater that was featured in 2001: A Space Odyssey as the crater where there was a moon base, right? And they looked at TMA1, which is Tycho magnetic anomaly. In Tycho, there was this black monolith that was inside of Tycho, right? So, you know, that was cool. Tycho was a very a smaller impactor, but it had a lot of energy, and so that's why its ray structure is so extensive. Now, one of the things that happens is it struck here in the highlands, okay, and you can see this apron around it of immediate ejecta, the immediate stuff that came out of it, but then the lighter stuff got flung thousands of miles. And how come we don't see rays in every single direction? Wouldn't you expect to see them in every direction? The answer is you would normally, but how come we don't? Well, the reason for that has to do with the fact that it struck in the highlands, okay? There are other high areas in here that shielded that material from going further and leaving a much larger and more extensive ray structure, right? All right, here we see material that actually landed in this crater, okay? And then we saw material way up here, right? Tycho's ray structure goes all the way up here. Isn't this crazy? That's a lot of ray structure. Look at it all, you know? Hundreds of miles. And that has to do with a lot of things. Now, if we actually go back to our trusty magnifying glass here and draw a line, let's draw a line right through Tycho, right here, and go, say, to here. And let's take a look at the terrain. Look at that. Okay, so right now, where's Tycho's center? There's the center of Tycho right there. There's the walls. But then out here we have another high spot. See this high spot? So that high spot right here from this other crater is something that could have caused this ray to be split in two like this. So we have two separate rays because there was those went around the shadow of the higher elevation. So we see that stuff happening too on the moon. It's really interesting how this all came to be, you know. And like I said, going back to our favorite pal Clavius, this crater, and again, if we want to know how big it is, we should just go and draw a line through that and get a rough idea. Okay, the distance through Clavius is just about 80 kilometers in size. And we also notice in Clavius that there's many craters. Here's like one right there. That pit right there, that crater goes down to minus 4,800 meters below the mean radius of the moon. But then climbs into the center, right? And we have a central peak area a little bit. And then we have all this complexity with this other crater here. So we got a lot going on, you know. So it's a really the tool is really fascinating to use, and you could spend days in here, absolute days, trying to figure out what's happening on the moon. And I have only touched the surface of the other layers in here that you could use. And so if you want to look, like I said, if you have craters that you want to look for, then if you know them by name, you type them in. Like one favorite one that people have is Pythagoras. Okay? Because Pythagoras was, by moon conspiracy guys, they like to say that Pythagoras is actually a crater with a gigantic gun sticking out of it. Yeah. This is the giant gun in Pythagoras. Now, admittedly, when you look at it from a certain way, a certain distance, okay, Pythagoras looks like it could have something sticking up, but then once you actually get into it and look at it the way that, we look at it and start to disassemble it using this system here, the LROC browser, QuickMap, you see that Pythagoras really is a mountain. It has a mountain in the middle. It's not a gun, right? And Pythagoras also has pretty steep hills. And sure enough, without fail, we have a number of trails where things have rolled downhill. Okay, and you can see dozens of them in here. Look at this. You can see how many things have rolled down the hill. Here's the boulder that came to rest here. It came down so fast it went bounce, airborne, bounce, airborne, bounce, 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 until finally it just careened here, or kept going and stopped here, uncertain. But maybe this rock is what stopped it, whatever. So you see the dynamicism here, the stuff that's going on, and the central peaks in these craters is where you're going to find a lot of these things, or in the walls of those simple craters, is where you're going to find these really neat stuff. So, honestly, it's really interesting how you can literally figure out the chronology of what happened in this region just by looking at the different things and how certain events overlaid other events. Like this crater was made, complex crater, right? But then this crater was a simple crater. This was made after the complex crater was made, right? Way after. I mean, because they had come to rest. Now, it could have been 10 years later, could have been 1 million years later, could have been 500 million years later. And how would we know the difference? We would tell the difference based on analysis of some of the debris, some of the rock types, studying what kind of minerals are here, and studying the ultraviolet radiation exposure that the rocks have had through other measurements that we do. We could determine how long this crater has been excavated and compare it to how long this crater was excavated around it, and then we can get a chronology for how long it was before this one was made, and so forth. So there's a lot of good science that we can do with this. See that? So now, again, this is stuff that sifted down to the bottom, and because this was a rounded bottom, and then it just filled in. Again, stuff rolling down, soil ejected from other meteorites striking came in, sifted down to the bottom for time. And this bottom filling also helps figure in age for the crater, because craters that are sharp-edged and don't have a lot of bottom fill are younger than these that are rounded over. If you've ever been at the beach and you made a sharp-edged sandcastle thing, and over time as the water hit it, it would start to round over and slump. That's what's happening here, but that's not water causing it. It's impacts from elsewhere that are causing it to shudder and shake, and maybe the sharp edges fell off and rolled into the middle. Okay, so the actual look of the crater determines a great deal about it. Okay, like here's one right here. This crater looks like it may be younger than the other one, but not by much. This has a lot of features that look like they might be still a little bit sharp. It's actually pretty soft, so it might not be as young as I thought. But again, it's just a fascinating survey of the moon. And again, to get here is very simple. You just go to Lunar Reconnaissance. You say LRO QuickMap in Google, and you'll get there right away. And all this stuff becomes available to you immediately. So I think that's really cool. And again, I'm staying in the 3D moon only because it gives you the option to then do some really cool things. Okay. And so I'm really pleased about it. So right now, okay, I've got it set up around Pythagoras, and I'm not touching it now, but we're orbiting Pythagoras, see? So Pythagoras is centered, and we're orbiting it. And over time, it'll slowly move us. It'll slowly move Pythagoras. You can see that it's rotating slowly. Pretty cool, huh? So yeah. So hey Mike Townsend, how you doing? Thank you for doing that. And again, like I said, if you guys can help us, we're trying to make our way here with Skytour Livestream, and we could use your help. If you can join the Patreon, great. Also, keep in mind that we do run contests here, and right now it's a very simple contest, and we give away things like telescopes, we give away binoculars, and we even give away, or looking to give away, night vision systems. Okay, and that's courtesy of Calabos, who's in the chat, and Tiffany. And Calabos and Tiffany are staunch supporters of STLS. In fact, we're their exclusive distributor for equipment. We've already given away a telescope and 2 pairs of binoculars, and there's more to come. And I think that's going to be a fixture of Skytour Livestream, is getting all of you equipment as best we can to start looking at the heavens yourself. So we're gonna work on that. As I mentioned, Calabos, whose name is Mike, and Tiffany and I and Marianne Robb are our chief financial officer. I'm the CEO of Skytour Livestream nonprofit, and she's the CFO. And then we have Tara Diulis in this with us, and together we try to bring you all the very best that we can of the night sky. I mentioned this before. We've got one telescope right now out in Arizona, and we have a second one going in. We're working on the location for this next one, and we're also working on what kind we're actually going to get. I was thinking of a certain size telescope, and I think I want to go bigger. So we're going to see if we can go bigger with the next telescope. All right, and that's something that could be just magical. Okay, here's another simple crater. You notice how it changed? That's because out here, when this photo was taken, the light was at a certain place. And then when we zoomed in, okay, the detail image of the crater showed that the light was at a different location. But it doesn't mean the data's not there. We go to our trusty magnifying glass, get our line and draw a line, and Now what we'll do, oops, I'm gonna just double click that. Double click to terminate, and you'll see our data is there. This crater happens to be minus 3,554 meters below zero, which is zero is the mean radius of the moon. Very cool, very cool. All right, now let's just pull the music down a little bit. I don't want to blast you guys out. Hey Curtis, how you doing? He says, 100%, man. Bigger is better. Yeah, that's true. And we're looking at it. You know, we need grants, right? Because we're a young stream and a young nonprofit. Look at the, see, here's the wall of the crater sticking up. Look at the shadow. Okay, look at that shadow. Isn't that cool? That's really neat. Now, interesting thing is knowing. Here's the thing. I used to teach this when I was teaching astronomy in a school setting, a classroom setting. I've taught kids. I've taught college kids. Everybody. Well, if you look at this shadow and how it looks, you look at the size of the shadow, and you can get a reasonable idea of how high this wall is from looking at the shadow and knowing the exact see James Hyde, I think you're onto this too. He says, can you measure the height of that crater? Yes, you can, and I'll show you how. You can get by looking at the shadows. You can actually calculate a lot. You can look at these shadows here, and depending on where the moon is, in terms of the sun rather, you can actually calculate a lot of data about the craters. But now with this tool, again, let's go back to here, and you see we want to know how big that wall is above the surrounding terrain. So let's go here, and let's do this, and we'll go only into the center, and we double click. And now, there we go. Watch you can see our little indicator there, that little indicator, the yellow indicator. Now it's at the very edge of the wall, and it's at minus 2,047, and then it drops steeply to the bottom of the crater, where it's minus 3,537. Difference between 3,537 and here shows you how deep the crater is. It's minus 2040. So it's like a 1,500 meter deep crater, right? And then from here, at the edge, right there, it tapers off gradually, all right, to where it then sort of levels out. And so from this level spot to here is where you'd calculate it. So where it seems to level out, I could have gone more. Okay, where it levels out here is at minus 2371, and then it reaches minus 2028. So what that tells you basically is that it's basically about 350 meters above the surrounding terrain. Right, that's the wall of the crater. And if you say, well, I want to see that, well, you can actually just kind of zoom in here, right, and level yourself out, and you can kind of see the wall of the crater right there. It's backlit, but that's neat, huh? I like that. See, that's what I like about this app. There's the wall of the crater. So you not only can measure it, you can actually see what it would be like if you were standing right there. That's cool. You have to be careful though, because you get down too low, and you'll end up going. You could go down into the base inside the moon. But that's what that would look like from right there. Neat, huh? And for those of you that have ever been at Messier Crater in Arizona, as you're driving to it on the highway from Flagstaff, you'll see Messier Crater, and it looks like that. You see that rim sticking up. It's very cool. Really cool. So there is this crater. It's actually pretty, and I'm going to get rid of our measurement line. We don't need that right now. Do we zoom back out now? So there's just one little crater, on the whole moon. That's one little crater that has an interesting, interesting history to it. Okay, maybe back out, and there we go. Now over here is another one of those volcanic rills. This is interesting. This is a rill here. This was a lava tube that has fully collapsed over the billions of years. There's a lot of these out there. A lot of these on the moon, and you can see some locations. You can see where the ground has subsided here, right? And then there's areas. Again, these are highlands. Okay, so it's really interesting how that all works. I want to show you another crater, which I think is pretty cool. So let's go back here, and where are we? We're at layers, okay, and we are in nomenclature, right? And then down below in nomenclature, there's a box where we can put in a name. We're going to put in Goclenius, and there we are, Goclenius crater. This is a neat crater. I'll show you why. Because Goclenius is riddled with a lot of these crazy features. Look at that. There's Goclenius crater, or Goclenius, some people say it. So there it is. That's a really interesting crater. It's got all kinds of these. Now that looks like a raised area, doesn't it? Okay, so let's change the view. All right. Okay, go that way, and okay, now you can see that it's a view. That it's like a rill that goes down, like that. So it's riddled with these areas here. So why is this more so than in other places? Well, it just has to do with the subterranean structure and how this particular crater was made. I think it's interesting when we look at craters like this. Now this crater is also. Let me see if I can. Let me do this. I want to pull us out here. There we go. So Goclenius also is a slightly elongated crater. I said there are some, and right next to it is a round crater, round crater, round crater, round crater. Okay, round craters. Okay, slightly elongated. So a slower energy impact. Okay, and the slower energy impact may have something to do with why there's so many of these areas in here that were generated by lava flow beneath the surface. James Dugan says collapsed lava tubes. Yes, indeed. That's something that has happened. Exactly so. And so these particular craters then have their own history and their own reasons for existing the way they do. So again, all right, when you look at these craters, you look at a crater like this one, and you say, well, wait, there's no central peak. Is it a complex crater? And the answer is, well, it does seem to have a terrace, but where's the central peak? The central peak could be buried by the lava that flooded into this crater. So you see, our identifications don't always show perfection and don't give us a perfect result. So now that said, we know that there's many different kinds of craters on the moon. We know that they're not the same depth at all. We know that they're not all perfectly round. Okay, we know that high-speed impacts will make perfectly round craters. We know that slow-speed impacts will make elongated craters. Right? We know that if we look at areas like this, okay, this is an area where there was a impact. You can see the basic round shape. Okay, that was a major size asteroid that struck here. And then these craters came later. However, this crater came before. And when this crater impact occurred, this lava flow from here spilled in to this crater, filling it. See? So it destroyed the wall of this crater and filled in. This crater came later because its apron here is flowing over this dark matter here. So this came later. This came later. Obviously, this came later. This, on the other hand, if we look at it very carefully, this is a crater that looks like it got filled in by the flood that occurred here. So this crater may have been here as a proud crater that had as much detail as one of these, but then the lava flooding here filled it in. Same here, filled in. Yet these all came later. So you can see, you can actually build a chronology of what happened just by studying the topography and how it all came together. Rays are another good way. Okay, when we look at Messier over here, okay, these rays are covering certain things, right? And so when they cover certain things, it means they are covering something that happened before it. And that's what we're seeing here. Here is an impact. We know this impact happened after this Mare was made. Why? Because we see a ray. We see rays radiating out. And they're covering the dark material. So this happened after. See? So we can build a timeline in history to what happened at that time. So that is that's really one of the neatest things we do. This is a beautiful Mare right here. Let's go see if we can get that illuminated. There we go. It's Mare Crisium. Okay, Mare Crisium is interesting because Mare Crisium, if you look closely, it doesn't have a whole lot of big craters in here, right? However, when you zoom in, okay, you can see that there's tons and tons of the little ones. Now, these happened over billions of years, obviously, all right? But some Mare aren't as pristine as Mare Crisium. Yes, these impacts happened later, of course, okay? But when we go like to, let's say, Mare Tranquillitatis, okay, this one here has also many, but we also see these round ridges here. See these round, like this round ridge? What is this? What's that round thing? Why is that kind of semicircular? But that is it's the ancient wall, most likely, of a crater that was then filled in by a subsequent impact, right? So Mare Tranquillitatis occurred. Then there was another impact here that made a crater that was probably like this. And then another impact occurred which flooded Mare Tranquillitatis again and filled this guy in. Again, building a chronology. It's really interesting. And I just like doing that. I like studying this to figure out how it all happened. You know? And then we have features like this on the moon that we talked about. Okay? It's like it's a scarp. And if we, I think this, either this is a scarp or I think it's a scarp. Let me see. I think so. So if we actually were to come here and draw a line through this guy. Remember, this is something you guys can all do now. Draw a line through this guy. You'll see that this is a scarp, and it actually goes from minus 750 meters below lunar mean radius all the way to the height, which is minus 486. So it's 300 some odd meters in height. But again, if you want to know what that's like, you can just zoom in the moon in 3D, drop down in here, and using the mouse wheel, use the central middle mouse button, and pull it around. Okay, and now you can see what that looks like. If you're going to climb it as an astronaut, that's what you'd be climbing. Right? So it's pretty cool. It allows you to actually see from a very, very different perspective what something that you can barely see in the telescope looks like up close. See that? So this is all well and good. And as I said, one other thing I wanted to make sure you remember is, if you haven't subscribed to us, please do. Join us, subscribe, and we will probably be giving away more equipment in the coming weeks and months, and you guys will benefit from that. It'll be everything from telescopes to binoculars, really good stuff. Let's go check Windy here and see. Yeah, well, see that? There's our observatory under the bell there. And we're getting some clouds out there. Yeah. Well, the other thing, too, that's nice is once we get our new webcam, our new all-sky cam in place, it's going to be really, really cool. We're going to be able to see all in beautiful color. I actually managed to... I managed to build a wonderful all-sky cam. I used a Raspberry Pi, and I used one of the ZWO cameras, purchased new, and it's a SkyTour Livestream all-sky cam. I'm going to make 2 more of them for each additional site, one here, and the 2 out in Arizona. We've got one in Arizona now, obviously, and that observatory is going to be joined by a second, and both of them are going to have these new all-sky cams. And they're full color, high resolution. You can see faint objects in this all-sky cam. And when you look, say, at the Orion's Belt and you look down below it, you can see the Orion Nebula, and you can actually see the structure of the nebula from the all-sky cam by zooming in. It's really cool, very, very high resolution. So we're really happy with this, really happy. And at the end of the night, it makes a time lapse, which we'll make available every single night for you to see. There's time lapse of how the previous night went. You'll see meteors, you'll see satellites, you'll see any oddities, and maybe you'll see UFOs possibly. So really cool stuff, coming our way, and we're just very happy to be able to do this for you guys. I do want to thank everybody that's here tonight enjoying this. And like I said, I'm the only one here tonight. I'm sorry if I'm unable to read all the comments. Curtis Horn, though, I see that. He says, what size are you considering? I'm actually, right now, I'm looking at some of the 14-inch packages. And that takes us right up around $10,000 just for the telescope and mount. Which is why it's really important to get some Patreon subscribers to get this. It doesn't benefit me personally. It's to our organization. Our organization benefits people around the world. We actually spend time. We've taught classes from our remote observatory. We've taught classes at various places in the world from that observatory, which is really cool. So we want to do more of that. We want to actually give access to schools and universities to our telescopes and take them on guided sessions where they can get some actual research data. And so that's part of what we want to do. We also want to create a mobile observatory system that we can take around the country, take to schools and universities, municipalities, museums, places where people congregate, and give them live in situ streams of the night sky using their own sky so they can see what's overhead, even in their light polluted skies. Because even if you're in a light polluted sky where you can only see the brightest stars, our systems can find all the deep nebula that are there hiding from sight. And the nice thing is that these objects that are over your head are objects that you could see given the right filter that you put in front of your camera. And so these are not that expensive to get. And it would bring all of this within reach of everyone that's here tonight watching. And perhaps one of the things you get from us, win from us, telescope or binoculars, you'll be able to spend time learning how you can use them. Now, one of the things, and then see some of these objects we're talking about, even from light polluted skies, because there are filters that you can use, and you can take pictures with your cell phones through binoculars, through telescopes, and it's very, very easy to do now. They've made that possible. Wow. Okay, so this said, I hope you guys are enjoying this and have enjoyed this. It's getting to the point now where I didn't expect to go this long because it's only the moon. But you got to see some really cool things, okay? You got to see some technology that is available to you right now, okay? This is the side that we see all the time, all right? And again, I'm in the 3D mode. But if we go, we can see our orthographic far side. This is the far side. See all those? Let me get rid of all the nomenclature right now. Let's just turn that off. You see how it's it's all lunar highlands here. But what's interesting is this area down here. This is called the Aitken Basin, Aitken Basin. It is an extremely complicated area, and it's a central depression followed by a concentric ring, followed by another outer crater. These rings are the things that, these rings are the result of major catastrophic impacts that occur, and that's sort of a frozen ripple in the splash, basically, of this a meteor. It was actually an asteroid. And there might be a remnant of this guy underneath here. There's an anomaly underneath this region. This is the lowest spot on the moon right here. How do we know? Well, we can go tell, can't we? Let's go take our tool and let's start drawing a line. Okay, and let's see if we can draw a line here. Let's just do that. Okay. And our line here shows us that we are minus 5,500 meters below the mean radius of the moon. Okay. This is the Aitken Basin. It's the lowest spot on the entire moon. Oddly enough, this impact was so catastrophic that it shifted terrain way out here. And somewhere out here, I'm trying to remember, it might be here. Let me check. Is the highest spot on the moon. It might be here. Let's go see if it's. Let's check this. I seem to remember it being kind of like here. Let's go see. Okay, yeah, look at the altitude here. Okay, watch this. Okay, so right there, at that point, all right, on the moon right there, it's 8,120 meters above the mean radius of the moon, and now it's even, this is 8308, and then this over here is even higher at 84, I just messed it up, sorry, right here, 8484, 8,484 meters above the mean radius of the moon. So the highest point on the moon is somewhere in this region. I may not have it exactly right. But the Aitken uplift, the Aitken Basin caused this uplift of this upper strata here north of it. And so the impact that made the deepest spot also made the highest spot. It's kind of a interesting finding, right? So that's what happened there with Aitken Basin. So let me do the nomenclature again. Let me go turn on our nomenclature. Doppler is the crater. It might be here. It might be right here. Now, it doesn't look like it had anything to do with this down here. I grant you. But the uplift that occurred because of this impact. It was so major that the whole moon basically shuddered. So it went boom and uplifted around the edges. And so that actually lifted areas, and the highest point of that uplift was right around here. And I don't remember if that was exactly it, but I kind of remember Doppler and this area right here. But it was actually the very highest spot on the moon, and they're both on the far side. Okay. Now you've noticed also, of course, that there's more craters on this far side than there are on the near side. And the question as to why that's the case is one that's been plaguing us for years, okay, hundreds of years, actually, several hundred years of staring at the moon. We only saw the far side of late, but since that point of being able to see the far side of the moon, I should say, one of the things that we're noticing is that there's more craters here than there are in the near side. When we go back to our map and we look at the orthographic near side, it's night and day. You see some highlands down here that might equal what you see on the other side. In fact, we'll just we'll do this in our lunar globe, because this is a better way to do it. Okay, so in our lunar globe here, we see that this side of the moon has these maria. Now, why would we see these flooding lava oceans here on this side, and over here, a tremendous amount of them? But then we get here, there's the Aitken Basin. We get here on the other side, and we see none. Why is that? Do you think it might have something to do with the fact that this near side is the one that's tidally locked to us, facing us? Okay, let's assume that. That's actually a good given, because it's night and day, right? You look at this side, you look at this side. Night and day, right? This is the side facing us. So we assume, we run with a hypothesis that says that the near side moon facing the Earth is full of these dark seas, these dark maria. And why would these maria form here versus here? What's different about here than here? Now, that's an answer, by the way, that could be a question you'd be asked to win some higher end equipment. But I will say this now. Jim Hyde says, okay, Earth pulling on it. Excellent guess, okay? But keep in mind that, yeah, there will be differential gravity, especially with a situation like this where it's tidally locked. Remember, this face of the moon always faced us. Always faced us. And so, but the gravity of the Earth is actually not the key factor potentially in this answer. And the reason goes back further when the moon was actually a lot closer to us, because this happened billions of years ago, well before the moon was 240,000 on average miles away from us. Okay, the moon was a lot closer, and so when the moon was a lot closer, we saw several things. We saw that there were times when we had bombardment of the Earth by asteroids, and the Earth was turned into a molten mass, and same with the moon. Okay. When the moon was a molten mass and the Earth was a molten mass, they were a lot closer to each other, orbiting much closer. The daytime here was probably 4 to 8 hours long because the moon was so close. Remember, the day got longer as the moon slowed the Earth down by tugging on the tidal bulge as it spirals away. And so when we look at the fact that when they finally cooled, the near side of our moon was, as it says, facing us, but there were still impacts occurring, right? As we can see, look at all of them, right? However, the Earth was also receiving impacts and made molten from time to time. And there's a lot of infrared energy that was being given off by this young, hot Earth. All right. And when that radiation has a force associated with it. There's a force due to radiation. It's called radiation pressure. And the infrared radiation, the pressure is much less than the pressure, say, from nuclear fusion, a star's light. However, it's still there. So what would happen is during the bombardments, when things would bombard the moon, what would end up happening is the stuff would fly up into the air, like the stuff that makes the rays for Copernicus later on in its history. But in the early days, that stuff would fly up, fly up into the space around the moon. And then the infrared radiation pressure, theoretically, was pushing it. And it would push it around the limb of the moon and push it past the near side and push it over the edge onto the far side, where it would deposit the ejecta from these millions of impacts. The net result is this side was thicker. Okay? So then, as the bombardments continued, this side of the moon was thinner. So big impacts like this one here would cause a puncture through this thin skin of the moon where it was still molten inside, and then the surface would flood with lava. The interior of Plato would flood with lava because the impact would puncture the thin skin of the moon on this side. So that was the going theory, still going theory, a working theory. These are why we have seas on the near side, because the skin of the moon was thinner. But wait, you might say, does that mean that the far side here, look at the difference, it's like half and half. The far side is actually thicker, yes. So the center of gravity of the moon isn't in the middle of the moon. No, it's not. It's farther toward the backside of the moon. Yes, it is. Oh, well, that's interesting. So if it's thicker on this side, it means that the impacts that occurred on this side, which were just as energetic as the impacts that occurred on this side, the impacts that occurred on this side, except for just a few, like Mare Moscoviense impact and Tchaikovsky, okay, these impacts couldn't puncture through into the still molten part of the inner part of the moon. And so they made just highland crater impacts. And that's part of the theory as to what may have happened to the moon and why the near side is thinner and thus more varied in its terrain than the far side that we see. Now, look at all these craters. Let's zoom in. Here we go. It's not just craters. It's craters within craters, on top of craters, next to craters, amongst other craters. It just goes on and on. And as always, we see this ubiquitous lines of pits from collapsed lava tubes that have occurred over here. All right? But we don't see them like we saw them on the other side. And that's because they were harder to come by on the far side than on the near side. The near side had way more of these, and they were a lot longer. Occasionally, we'd see a longer lava tube that would collapse on this side. But for the most part, this area on the far side was composed of much more solid rock, thicker rock, right? And so any lava tubes were going to be shorter in length, whereas on the near side, we have lava tubes that run for hundreds of miles, right? So that's pretty interesting. Mare Moscoviense is a rare location where we actually had an impact that was big enough to puncture and thus also cause lava tubes and collapsed lava tubes to occur here in a secondary crater next to it. So there's a lot of history on this side of the moon. Just amazing. So tonight was meant to be like a history of the moon and a way to think about potentially what different features on the moon look like, where they came from, what tools can we use, and that's where we have these tools here. Okay, so if we draw a line through from one spot on this far side to just another spot, and you look at the difference in the craters, look at this. They're all positive numbers. No negative numbers below the mean radius, right? They're all positive because these are highlands. And let's look at Mare Moscoviense. Is Mare Moscoviense an area where there's going to be an area below? Let's find out. Okay. Here, Mare Moscoviense, because of the puncture that occurred, the bottom of Mare Moscoviense has minus 3,200 feet, right? But then you quickly rise up to a positive number outside of it as you can see the yellow indicator there. Okay, now we're back to the highlands again. And so this is what we see on the far side of the moon. It's much thicker over here. It's much denser. And so the moon is actually, as far as astronomers are concerned, the moon is kind of football shaped. Yes, it looks round, but it actually has a center of mass that makes it oblong. All right. And that's something that's interesting too, because it could make the moon unstable if it ever had a massive impact, and maybe the moon could flip around and the far side would face us and be tidally locked again, you know. But that's only if it had a major impact, and if it's getting a major impact, it means we are too, so it wouldn't be too much fun. Okay, so we go from the thin walled side of the moon to the thicker stuff, and it's interesting how the separation is almost too perfect between the exact side facing us and the side that's not. Clearly, the fact that it's facing us is part of the reason why this surface was so thin. And that's why the theory about the infrared radiation from the Earth pushing that material over to the far side. Because remember, when an impact would occur, this stuff would go way out into what we call the exosphere. There's no atmosphere, so the exosphere, the area around the airless body. And then the infrared radiation could gently push it around to the other side, where the moon's gravity would allow it to then fall back and build up the other side. That's kind of the possibility that we're seeing here. So I think that that's probably a reasonable explanation for what we're seeing and why the moon looks the way it does. So, and Izabela, I'm sorry, I know that that's going to make this table of contents for this stream just crazy for you, and I'm sorry about that. I will I'll do my best to wrap it up now, because I know I've gone on, but it's just so much to see here. And last, like I said, I just want to point out one more time, if you are interested in 3D printing any of these craters, one more time I'll show you how to do it. Okay, first of all, let's get rid of all of our previous data that we put up here. Okay, so you basically go to you're going to start off like it probably here, and you're going to have all these layers. You can say, oh no, where do I go? You go to the magnifying glass, and then you have this guy. You take this guy, and you start drawing a line, and here to here, draw it here. You see it's drawing out a shape now, a volume. Okay, and then you can bring it up and go to, make it like a squarish looking shape. And now you have this square shape, right? This square shape is actually a very nice shape. You notice the moon is curved, so you're going to see this curvature, okay? That will be represented in your 3D model. And now, once you have that, you'll say, well, now what do I do? Well, you have your feature info over here. It tells you about the thing. It tells you how many square kilometers are in it, 37,201 square kilometers within this square, if that's interesting to you. And you can say, well, we can inspect every single datum, every single element of data from all the many missions. Okay, you can see which ones are meaningful here. But then you can also do a search for any of those products within here. And then you go to Other. And, of course, you have age units, you have other observations, and so forth. But 3D printing is the one you want. And now when you go to 3D printing, it's like, whoa, look out. Whoa, there's Plato. It looks like a 3D image. It's because it is. Now you can export Plato as a 3D image, okay, as a 3D object. It'll come out in a STL file format, and STL stands for stereo lithography. And when you build the model, it's going to build it right here and then give you a link, and you download this link. It'll be in a zip file. Double click on it. When you double click on it, you'll see a .stl file in there. That's your GRO file. That's what you send to your 3D printer. Then you can also, and you'd have to, if you change this value here to say like 2, it exaggerates the vertical by 2, as you see it right there. Okay, and I'm just scrolling in to show you this, right? But you want to be careful with this, because if you do it too much, it ruins the image, and it could screw up the GRO. Like, that's definitely this. This is how Chesley Bonestell, an earlier artist that made imaging of the moon for books and so forth, this is what he thought the moon actually looked like, was this really high mountains and sharp peaks. In fact, through all the impacts, the moon has actually been softened, and that's why we see this looking like this. Okay, so now this is how you get your 3D models, and then you can send them to your 3D printer, and you can print out your own plates of craters if you want. Now, if you don't have any of this, if you don't have a 3D printer, not to worry, because we can do this for you. And that's kind of our goal, is to bring you things in Skyter live stream that you can't get at yourselves easily. But if you can, we're going to make sure you see how you can, and we're going to show it to you. And that's just what we've done here. So there you go. This is our Lunar Reconnaissance Orbiter QuickMap night, where you get to see all these crazy things happening right before your eyes. And I hope you enjoyed it. And yes, this is kind of a lecture, isn't it? So I apologize. But it's a familiarity lecture to show you about all these different available data sets and things you can do things with. Now, just remember, take your amazing mouse and just scroll right in to a crater that you don't even know. Okay, actually, that looks familiar. That's not Euclid, is it? I don't even know. Let me click on this. It doesn't. This sort of looks like it, but it doesn't. We'll find out. Okay, Menelaus. Okay, and you zoom in, and then you get the better data as you zoom in. And now down here, remember, okay, if we look down below, it shows you how many meters per pixel you're seeing. This is the resolution. And you go in further and further and further, and you can go in quite a lot. We're at now 3 meters per pixel. You can go technically to 0.5 meter per pixel, and that's kind of where it really ends. With this particular thing, we're at 0.43, right? And you're not going to see it as clear, although that is pretty clear. They've actually upgraded a lot of the data in here. So this gives us a beautiful scale. We're inside this crater now. We're inside Messier Crater, and we can pull ourselves out of it and say, "Wow, look at the walls of this crater from inside of it. This is crazy." This is why it's so neat, and this is why it's so easy, so much fun to do this lunar exploration here. There's very few places, by the way, where you won't find data available. There has been data acquired for every square inch of the moon. So when people say, we didn't really go to the moon, earlier tonight we saw the Apollo landing sites. Hello. And where do you find those again? Well, you actually would come out of overlays here and look down this major list of stuff, and you'll see, actually I think overlays is where it is. Let's get rid of nomenclature right here for a second and close it up. And then you'll see anthropogenic features. Anthropogenic features. These are human-made features, right? So when you click on them, you'll see red dots appear on the screen where we have landing sites and so forth. All right, and so as you zoom out, you'll actually see them show up, right, on the moon. Then when you zoom into them, you can see things like the Apollo missions details. Okay, this one's kind of fun. This is it's gonna be hard to see. Let me back out just to find it again because there it is. This right here. I'm gonna just keep zooming in and look for a relatively recent crater down in here, because the Ranger missions were sent to the moon, and what those were, before we could land on the moon, we just impacted the moon at high speed, right? And so we zoom in here, and Ranger 8, okay, Ranger 8 crashed right here. Okay, it's a little bit pixelated because it's not the best, and when we go into anthropogenic features, we can actually knock the opacity down a little bit, and that's supposed to actually be getting dimmer, but sometimes it doesn't. But once this comes back, it should be fine. And so when you see the Ranger 8 impact site, okay, you see that right in here, Ranger 8 struck. And where's the crater for it? Well, let me see if I can actually get that to show. I want it to show. Yeah, this is it. Not that. That's actually not it. You notice when you look here, that's the newest crater in the whole area. So this is the Ranger 8 impact crater. And if we take it a step further, like we always do, go back and get a little indicator. We just push it here and put it there. It's a 10.3 meter crater that the Ranger space probe made when it struck the moon. So that was pretty cool. That's a really cool. So this is the impact site of the Ranger 6. And it took pictures all the way down to the moon and then smashed itself into oblivion. Okay. And that's what the Rangers did. And crazy, yeah. And so you see that. And there's imagery. You can look up Ranger, the Ranger program, and see all the photographs they snapped as they made their way in their terminal descent to the moon's surface, where they were obliterated in a blaze of glory. Then we have others. Okay. Obviously, I won't be taking you through every one of them, but you know. This is Surveyor 5. You can't miss it. There's Surveyor 5. This is the spacecraft that made a soft landing on the moon. And when did Surveyor 5 do that? Let's see. Does it tell us? It just tells us this. It tells us the latitude and longitude. It doesn't tell us anything else about when, but you could look up Surveyor 5 and get that information. But that landed right there at that point on the moon. So after the Ranger space program, we figured out how to soft land on the moon. And then the Surveyor series came along, and we landed on the moon with the Surveyors. And we kept doing that to find some of the really cool landing sites that might be a special place for us. And now this, what's this? Let's see where we are here. Oh, hello. Is that actually Apollo 11? Is that Mare Tranquillitatis? Is that where we are? We may be in the Sea of Tranquility. It looks like we are. Yeah, so that's Apollo 11, the very first landing site on the moon. Interesting about this site, when you look at it, okay, here's a lunar module, okay, and this is as far as they walked, because they only could walk, they couldn't do anything else. Okay, so there's the base of the lunar module, the shadow, okay, and then the retro reflector array, which I told you about. It's got those big, it's a big panel about 4 feet by 4 feet in size, and it's got all these tiny little reflectors in it. That was made, as I said, at my university where I got my degree in astronomy, and we're very proud of that, like I said. And it measures the distance to the moon very, very accurately. Okay, but if you notice, that's a very, very tiny distance, and you can't even see footprints. Okay, because this was the first time they were there, so they did a few excursions on the moon, not too many, and they ended up basically, actually, they had a 1201 alarm when they went to land, and they actually had to land manually because the computer just like went and it couldn't land. So Neil Armstrong had to navigate it to the moon by hand, but they had trained for that, just in case it happened. They trained for that. So there's Apollo 11. Very, very cool. Yep. And it's no surprise that it's near the surveyor sites. These are sites where they're trying to, figure out where the best manned landing sites would be. Okay, Ranger was a really good program to actually just see the moon close up for the first time, just like the Mariners were for Mars. Now, Russia was no stranger to the moon, and they made the Lunokhod rovers, which actually landed on the moon and kind of rolled around, actually. Pretty cool. This is Luna 21, and as we zoom in, let's see if we can see it. There's Luna 21 right there. All right. Pretty, right, that little tiny white thing, that's it. Okay. It looked like a little tiny golf cart, kind of a thing. A really good feature, a really good feature to be able to move around on the moon. They're among the first to do that. So very happy for them for doing that, actually. Good for us. Now here's another one, Lunokhod 2. Okay, Lunokhod 2. There it is. Very obviously. All right. Actually, look up Luna and Lunokhod. They're two different missions. So you can do this for hours. You can just go through all the missions from all the countries that got there, including us and so forth. Just amazing. Now, and then wherever you see, again, we in our settings here, we have anthropogenic features, human-made features selected. So you zoom out and like what's this? Okay, well, you come down here and you see, well, this is one of ours, one of theirs. Whose is it? Bereshit. All right, well, what is that? We'd have to look that up to find out. Bereshit. It's an impact site. So that's actually a crashed object. A crashed site right there. I forget which one that was. Some of you in chat might know. But I remember, was that the Indian or Israeli one that crashed? I'm not sure. Not sure. Anyway, so again, pulling out from the moon, you can just zip back around and go to all these other places on the moon. Notice how when we zoom in, by the way, you see what looks like, oh, it's nice and smooth. Zoom in, and it becomes anything but smooth once you get in there. Okay? It's actually quite bumpy, and it'd be really dangerous to try and land there, right? Because those plains aren't really plains. They're full of craters. So that's actually pretty bad, That's not the kind of place you want to go. All right, so backing out a little more, let's go find some other places. Ooh, look at this. There's something very interesting happening in there. I think I know what this is. This Apollo 17? This might be Apollo 17. Oh, Apollo 15. Okay, my mistake. So we get on to Apollo 15. And LM means Lunar Module. There it is. Okay. LRV, Lunar Rover. There's a lunar rover at the end of the trail there. Okay. And because we're in 3D mode, we can zoom in way more than the 0.5 meters per pixel. This is how much you can zoom in. It's just a little less than this. Okay, let's see, right about here. This is about how much you can zoom in when you're just doing it with the orthographic nearside features. Okay. So these are all the prints from Lunar 15, Apollo 15. Look how far, when you get a rover, look how far out they went. That's pretty good. So you say, well, how far is that, Mark? Okay, that's easy. How do we do it? Go to your magnifying glass, grab that line, and say, well, here's the lunar module. And they went out to here. So how far did they go? 0.13 kilometers. Okay, that's how far they went. Right? And really, what does that mean? That means 130 meters, right? So that's 130 meters is like, 300 and some odd feet, 330 feet or whatever. So they actually went pretty far from the lunar module here, all right? And then they put the ALSEP in, 0.1 kilometers. The retroreflector array was 0.14. So you see they're staying kind of in the same range all around this central area. And what drove that? Well, what drove that was the fact that they had time for only a certain amount of lunar exposure because of their backpacks. Because we're turtles, we carried our oxygen and everything that we need to live with us on the moon. So we had to do that. So, really interesting. Okay, so that said, so that's Apollo 15. Let me just get rid of that. So we zoom out now, and all right, that's Hadley Rill and everything we talked about before. Okay, and so as we back out and we do this, get this oriented right, because that's about right with north up. So we can actually now pull away, and as we move around, you can see other sites that we've been to, other places that we've gone to. Okay, that's another laser ranging location. These are all okay, that's interesting. This is the Chinese mission Chang'e 3. So we zoom into this. Okay, Chang'e 3 is right here. Chang'e 3 rover. So that's the Chinese mission. They went there. Okay, the U2 rover is there. And that was on this location on the moon. And if we zoom out, you see where that was exactly in terms of location. It's in the middle of a sea, or a Mare. It's south of Plato, and in Mare Imbrium here. All right. And now, so I won't just take you through all of them. I'm just going to say you can just put these all in and get a great idea of what missions were what and where they were. Very, very cool stuff. Okay. And let's see. Let me come down here and see which this one is. That's Surveyor 6. Okay. And, okay, this guy, I was trying to find it before. Is this the one? Probably not. I'd see more than one thing here. That's a Ranger impact site. Let's go see if we can see any kind of details. Okay, Ranger 9. So Ranger 9 struck right here. That's its impact crater that it made. Ranger 9 was the photographic missions where they just went to the moon and took pictures until they impacted and couldn't take pictures anymore. Okay. Again, really neat collapsed lava tubes. Look at that. A string of these pits. Very, very cool. Oh yeah, alright, let's see here. As long as I can see the red, I know I still got the ability to check this out. I know that there is a... Which one is that one? That's Apollo 16. I think we looked at that already. Well, maybe what I can do as a last thing is go back in here and tell it to look at this and see if I can see that one tag. Is that actually Apollo 17? The last Apollo mission, is that the one? Okay, why is it saying Apollo 16? I thought we just saw that elsewhere. Okay. Interesting. Wonder if some things are cross-linked in the data. Maybe they are, maybe they're not. Let's see here. We got Chang 5. We have the others. We have all kinds of missions you can go through and see all the different locations. Okay, bear sheet, yeah. I saw Apollo 17 was in Highlands somewhere. Okay, that's actually an image that you can download to see what's going on here. So if you say Apollo 17... Okay, well anyway, not to belabor it. Alright, so you get the idea, and this is actually a lot of fun to go through. You can lose days in here. Ask me, I know. And the 3D globe is the best one. Alright, so that's the Lunar Reconnaissance Orbiter QuickMap, guys. And I think that you guys will have lots of fun with this. You'll have a great time trying to figure out what everything is and searching for stuff. So I hope you enjoyed this. I'm going to call it quits for now. My voice made it, which is great. Yay! And if you guys have any questions, remember, go to skytourlive.org and you can find your way to... Oh, that's the Apollo 17 landing site there. Okay, well, we can zoom in further when we get to the actual one on the moon. So that said, you can actually reach us by going here, skytourlive.org or skytourlive.com. Join our stream by going to Skytour Livestream, okay, which takes you to here, which is, oh look, a live stream is happening right now. I wonder what that is. And you could get there that way to our live stream and join. It's free. Or you can go to our Patreon page. Now, on our Patreon page, we have a number of memberships. We have a Star Watcher for $3 a month, Stargazer for $5 a month, $10 a month for the Observer. That's a very popular one. Most popular, I guess, is that one. Then we have Astro Geek for $25 a month. We actually have a couple of those. We have $100 a month. I know people are saying, who'd do that? Well, there are people that have done that and are doing it. And then STLS Lifer for $200 a month. But we're looking for people that want to join us at $3 a month level. And if you're with us for 6 months, it'll put you in the running for the Aurora Sport or its successor, night vision, full color night vision system. And I have one. It's stunning. You can literally see satellites galore in full color. You can actually see the star colors are beautifully. And by the way, record it and record all the video you see. You can run that with your Wi-Fi and put it on your screen and run it through Wi-Fi and enjoy it through Wi-Fi. It's really cool. I've used it to do meteor watches and stuck it on a tripod, plugged in the adapter so it would run for hours and hours and hours. And it's really cool. So join us at $3 a month to be in the running for that. Anyone who's joined us in these higher tiers are automatically included in that as well. Okay, so we'll do that, but only Patreon subscribers can participate in that particular giveaway for the Aurora Sport. All right, but anyway, we're here, and if you want to learn about us, you can come here and see this. Check out our cool pictures. It takes you to the online database. These are the telescope that we give away with Calabos and Tiffany. JSCO 77 won this telescope on 1220. Mind Remote 7 won a pair of Celestron binoculars. And the Goblin, who visited us for the first time, his first time in the stream, he won the Celestron binoculars. All right. So you see, no matter who you are, you come here. You have to be a member, by the way, to participate in these. You don't have to be a Patreon subscriber, just a member to participate in these giveaways. Okay, we don't do this for anyone other than people who subscribe to SkyTour Livestream, and that's free, right? You want actual photographic prints, whether printed on canvas, on aluminum sheet, or under glass, unframed, or just plain prints, you get them here. Okay, our photo gallery is here. You can see some of the things we've done. This gives you a little idea of what we do, and you connect with us on X, on Instagram, Facebook, and of course YouTube. And if you want to go visit our SkyTour shop and check out what we do, if you look at this, you go SkyTour shop store, and well, now you can see all the things that we put on all of our look. You want socks? You want socks? You've got socks. You want a big blanket, a big throw blanket? Oh, these things are so warm. It feels so good. I know a lot of people that have bought these bags. Okay, many people have bought these tumblers. Okay, all this money goes to support us. You want a moon clock? How about Horsehead Nebula sneakers? How about a lamp? Okay, a water bottle, cards, a deck of cards. I got a pair of those, set of those right here. Okay, iPhone resistant or iPhone impact resistant case. Okay, just gotta say which iPhone you got. Travel bags, so cool. And like I said, we got women's and men's sneakers. A Rosette Nebula clock, we have that too. I want for your Apple Watch. You want a watch band? It has our stuff on it. There you go. Mugs, of course. And if you have a dog, we have several different kinds of pet bandanas. Yeah. So, and this is just the beginning. You know, this is about 50 items so far that we have out there, and that you can again find from our portal under more. So here you go. You start here, and all things SkyTour begins from there. So I want to thank you guys for joining us tonight. Please do subscribe, join us, spend time. It's all free. You want to support us in Patreon? That's wonderful. $3 gets you in on the $3 a month for 6 months gets you in on the night vision system giveaway. Would love to have you with us. Love to have you join the family. We have over 8,100 subscribers now. We want thousands more because we'd like to be able to spread this to the world. So spread this to the world. Tell all your friends, and give us a shot, because you know what? No one else is doing this. No one's doing this. With our live telescope feeds, no one's doing this. So you guys, you have a good night. I really hope to see you again in the SkyTour live stream. I suspect I will. And I will be back, and hopefully it'll be clear. Let's just do one more check out there. Oh, yeah. See, we got this thing coming through here. It's really, really crazy. These clouds coming through make it so difficult. That's our observatory out there in the middle of the Arizona desert, far from any lights. And, of course, we have clouds coming through. It's rare, actually. We have 300 clear nights a year, so I don't know why this happens, but it does happen. So that said, you guys have a good night, and we will be back on the next clear night, which hopefully will be tomorrow night. Shh. Okay. So we'll see you guys. Thank you for joining me on this beautiful lunar mission tonight. Remember, Lunar Reconnaissance Orbiter QuickMap. All right. If you look it up in Google, it'll bring you right here, and then you can have fun and play as well. So long, folks. We'll talk to you tomorrow night. Hopefully. Well, maybe another night, but you know what I mean. All right. We'll see you.